वेरी गुड मॉर्निंग टू ऑल ऑफ यू। आप सभी का बहुत बहुत स्वागत है इस कॉन्फ्रेंस में। और दीप प्रज्वलन के साथ में हम अब इस कॉन्फ्रेंस की शुरुआत करते हैं। और इस कड़ी में मैं सबसे पहले हमारे संस्थान के आदरणीय प्राचार्य प्रोफेसर एसपी शर्मा जी को आमंत्रित करते हैं कि वो सभी का स्वागत करें।
National Academy of Science India, Honorable Dr. R.G. Sharma ji, Emeritus Scientist, IUAC, New Delhi, Honorable Professor C.K. Ghosh, former Regional Director, IGNOU, New Delhi, Dean of Instruction, Dean Research, all heads, faculty members, students, and distinguished dear participants. Good morning and warm welcome to all of you. I'm really grateful to our chief guest, Dr. Kishan Lal ji, and guest of honor, Professor Ajay Ghatak ji, for sparing their valuable time to be a part of this inaugural session of this conference on emerging trends in physics and physics education. Sir, a very warm welcome to both of you. Friends, as you are aware that National Education Policy 2020 envisages for the reforming curriculum and pedagogy in schools to make space for critical thinking, creativity, multidisciplinary, holistic, and analysis-based learning in view of Indian tradition and value system. Physics is a subject which deals with subtlest aspects of nature and is backbone of sciences. It has been evolved through a great gene in presence of previous few centuries and even more in recent past with the emerging disruptive technology. Research in physics at fundamental level is very fascinating and requires meaningful learning of the concept of physics. Effective physics education is a key to success for any advancement in physics. Keeping in view the close link between physics and physics education, present conference planned with an attempt to provide a common platform to teachers, teacher educators, experts, educationists, researchers, and other academicians for sharing their ideas, researches, experiments, best practices, and innovations, and having opportunity to discuss and deliberate on emerging trends in physics and physics education in the context to ancient Indian scientific knowledge and its relevance to current scenario.
Thank you very much, Principal Sir. Right time to just give some background about this conference, and then we will start the representations of our eminent speakers. So, as Principal Sir told, that it's in the light of National Education Policy 2020 that we require some new ways of conducting curricula, and in fact new pedagogies and use of disruptive technologies. So keeping this in view, we have planned for this conference. So objective of this conference is to provide a forum to physics and physics education researchers, teachers, and teacher educators to share their research work, innovative practices, and emerging trends in physics education. And then to make recommendations for future course of action for the promotion of quality school education in general and physics education in particular. To document the best practices and researches in the field of physics and physics education, and to disseminate the same with the stakeholders, and to encourage research in physics and physics education in view of different aspects of NEP 2020. So we hope that deliberations made during this conference and presentations to be made by the participants will be very vibrant and very lively discussions will happen on this platform. So with this, now we are in a stage of releasing this souvenir of this conference and
Yes, we can see the screen.
Yes, the screen is shared and we can see it
We
loud,
can,
very clearly.
we can see the screen. We can see the screen.
okay, thank you, Chief Guest, Guest of Honor. And now, without any delay, I invite chairperson and co-chairperson of this session to start this session with the introduction of our distinguished speakers. So it's over to chairperson and co-chairperson.
Is there any technical problem? If it is so that we can introduce from here itself. Okay. Now let me introduce our honorable guest of honor, Professor Ajay Ghatak ji. Professor Ghatak ji is retired from IIT Delhi.
Am I audible?
As Professor of Physics, and currently he is President of the National Academy of Sciences, the oldest science academy in India. He has research interest in fiber optics and quantum mechanics. He has authored several books, including his undergraduate text on optics, which has been translated to Chinese and Persian. He is recipient of several awards, including 2008 SPIE Educator Award in recognition of his unparalleled global contribution to the field of fiber optics research. And he tireless dedication to optics education worldwide, and also the CSIR SS Bhatnagar Award. Without taking much time, I request to Professor Ghatak ji to kindly deliberate on the topic. Professor Ghatak, sir.
Thank you, Professor Sharma. Thank you very much. Let me share my screen. Yeah. ये क्या हो गया? Oh. Can you see the first slide, please?
Yes, it is visible, sir.
Okay, thank you very much for your kind invitation to give this talk. According to the program, I'm going to speak for about 20-25 minutes, but actually the talk is slightly longer. It's about 40 minutes. I will try to condense it as much as possible. So I'm very happy to see this initiative on the part of Regional Institute of Education. I'm going to talk about 10 beautiful experiments in physics. This is going to be an elementary talk, primarily meant for young students to enthuse them to do new experiments. In Professor Robert Crees, some time back, I'm sorry, he was born in 1953, is a philosopher and historian of science. In 2002, about 20 years back, Professor Crees asked physicists to nominate the most beautiful experiment of all time. And from that emerged a list of 10 most beautiful experiments in science. So the experiments जो मैं describe करने जा रहा हूँ, वो मेरे experiments नहीं है, मेरे choose किए हुए नहीं हैं. These are the 10 most beautiful experiments in science and not in physics. जो Professor Crees ने लोगों का पोल करके नॉमिनेशन करके ये चूज किया है. So the last in the list, the 10th experiment, is on Foucault's pendulum, which demonstrated the rotational motion of the Earth, and it was carried out in the year 1851. So देखिए, this is the Earth, which is rotating about this north-south axis, and of course this is the equator. So because the equator, a point on the equator, as the Earth is spinning around, traverses a greater distance, the linear velocity of the point A is much greater than the linear velocity at the point B. The linear velocity at the equator is about half a kilometer per second, whereas at a latitude of 60 degrees, it is about quarter of a kilometer per second. So now I throw a cannonball directly to the north from the equator, let us suppose. So this has a lateral velocity of about half a kilometer per second. So by the time it reaches the point B, so the point B, because it has a smaller lateral velocity, it reaches the point B prime, and the point D, the cannonball itself, reaches the point D prime. This is known as the Coriolis effect and demonstrates and happens because of the rotation of the Earth. So in 1851, Leon Foucault suspended a 67 meter long wire, and at the bottom of it there was a spherical brass coated lead ball weighing 28 kilograms. And as it oscillated, as this pendulum was made to oscillate, because of the rotation of the Earth, because of the Coriolis effect, the plane rotated. And it's a very beautiful experiment. And there is this beautiful video on YouTube where they show the slight rotation of the plane of oscillation in the clockwise direction of the Foucault pendulum at the Chicago Museum of Science and Industry. I wanted to show the video myself, but it would have taken a lot of time. So you see, this is at the point 6 minutes and 18 seconds, and it is still just as it oscillates, the Foucault's pendulum oscillate, it is just near this fin. अब देखिए थोड़ी देर बाद 6:35 पर ये इसको गिरा देते. So the plane of the pendulum rotates, and that is because of the Coriolis effect that is there. So this is considered to be the 10th most beautiful experiment in physics. Foucault's pendulum is also at the Ranchi Science Center and at several places in India. So at the latitude of Ranchi, the pendulum's path rotates by about 6 degrees per hour in the clockwise direction. A Foucault's pendulum in Sydney, in Australia, will rotate in the anti-clockwise direction. So this is a very beautiful experiment showing the rotation of the Earth. Next experiment, ninth experiment, is by studying the scattering of alpha particles by thin films of gold. Ernest Rutherford, who is considered father of nuclear physics, discovered the tiny atomic nucleus, that the atomic nucleus was indeed tiny. So what is scattering? The scattering, for example, here is an interstellar object coming from a long distance in the vicinity of the sun. It changes the direction. So actually the path is a hyperbola. The sun is at the focus, and this phenomenon is known as scattering. Similarly, if you have a positively charged alpha particle seeing a nucleus, a positively charged nucleus, then it will get repelled by it, and there also it will get scattered. The trajectory is again a hyperbola, as you must have done in your classical mechanics course, and this phenomenon is known as scattering. In the previous case, it was an attractive force. In this case, it's a repulsive force. So this is the impact parameter, and Z1Q is the charge on the alpha particle, Z1 is 2, and Z2Q is the charge of the gold nucleus, let us suppose. E is the energy of the alpha particle, and epsilon naught is the dielectric permittivity of free space. This is derived in any book on classical mechanics, like the book by this thing. So the experiment was carried out by Geiger and Marsden at the suggestion of Ernest Rutherford. So the experiment was that this was a radioactive source emitting alpha particles. The alpha particles were also discovered by Rutherford, and a few years earlier. So he allowed the alpha particles to fall on a very thin gold foil. And what he found was that the alpha particles underwent a very large angle scattering. They were detected by these fluorescent screen. And so if you observe complete backscattering of alpha particles, so here is an alpha particle. Let us suppose this energy at a very far away distance is E alpha, and the potential energy is 0. Then it approaches, it gets repelled by the nucleus. It is inside the atom. It is inside the atom. So it is not seeing the electron. So it gets repelled by the nucleus, and then it stops and it goes back. That is how a complete backscattering occurs. So when it stops in the classical model of scattering, the kinetic energy is 0, and this is the potential energy. So this quantity must be equal to this in quantity because of the conservation of energy. So this quantity will be equal to this, from which you can calculate the minimum distance of approach. So if I write Z1 is equal to 2 for alpha particle, Z2 is equal to 79 for the gold nucleus, and the energy of the alpha particle that Rutherford used was Geiger-Marsden used was 5.3 MeV. If you substitute it, it is 44 into 10 to the power of minus 515 meters. So it is 44 femtometer. So understand, because they observed complete backscattering, that means that this R minimum is greater than the radius of the nucleus, The size of the nucleus must be less than 40 femtometers. 1 femtometer is 10 to the power of minus 15 meters. So the size of the atom is 10 to the power of minus 10 meters. 10 meters, and the size of the nucleus should be much less than that. And that was the great prediction that was made by this thing, because if it enters the nucleus, once it enters the nucleus, it will just pass through, because this is the potential energy that is seen by the alpha particle This is the Coulomb repulsion, and because it is if you assume the gold nucleus to be uniformly positively charged, then the potential energy will be zero, will be decreasing, and so therefore it will just pass through the nucleus. So this was the J.J. Thomson's model of the atom, that the atom consists of a positively charged body in which there are electrons, and so this is known as the plum pudding model of the atom, which was put forward by J.J. Thomson. The atoms are assumed to be uniform spheres of positively charged matter in which electrons are embedded. If this model would be correct, alpha particles should have passed through the foil with very little scattering. So Rutherford's famous experiment established the radius of that the nucleus is very tiny. Okay, let me skip this. And he received he's considered as the father of nuclear physics, but he received the 1908 Nobel Prize in chemistry. Many feel that he should have also received the Nobel Prize in physics. The next experiment in the list is Galileo's experiment. Galileo, as you know, was before Newton. Newton was born in the year 1642. So he was not aware of Newton's laws of motion. So Galileo's experiment showed that the distance traversed by objects sliding down inclined planes is proportional to the square of the time. So this distance is proportional to t square. As you know, Newton's law say S is equal to ut plus f half at square. So u is 0, so S is equal to half ft square. But Galileo did not know of that equation. So he, by experimentation, found out that the distance is proportional to the square of the time. And how did he measure time? So he took a huge bucket of water, and a very big bucket of water, and the time that it took for the object to slide down, he measured by the quantity of water that is received in this small bucket. So there is a very nice small diameter hole that is here, and the water comes out, and the amount of water that is collected is a reflection of the time that is there. So from this, he calculated the distance and the time and plotted it and found that S is proportional to t square. So this is actually using, as I mentioned, using the Newton's laws of motion. So what Galileo found was this distance that is traversed is proportional to the square of the time. And Robert Crease writes in his famous book that in many respects, it was the first modern scientific experiment in which an investigator systematically planned, staged, and observed a series of actions in order to describe a mathematical law. So this is one of the most beautiful experiments in science. The next experiment in the list is the experiment of Eratosthenes in 3rd century BC, about 2,300 years back, that he measured the Earth's circumference by measuring the length of a shadow. And what he did was that, you see, on the Tropic of Cancer, there is no shadow on June 21 around noontime. So rays hit normally, parallel rays from the distant sun hitting normally on the Tropic of Cancer on June 21 around noontime. So this is known as the starting of the summer solstice. So in India, the Tropic of Cancer passes through 8 states: Gujarat, Rajasthan, Madhya Pradesh, Chhattisgarh, Jharkhand, West Bengal, Tripura, and Mizoram. And on the Tropic of Cancer, on June 21, this is the Tropic of Cancer in Madhya Pradesh. And Ujjain, which is in Madhya Pradesh, is a vanishing of shadow at the observatory in Ujjain on June 21, 2018 at 12:28 p.m. The observatory was constructed by Maharaja Jai Singh of Jaipur. So you see, at 12:28, and it's a very big tourist students attraction, that the shadow completely disappears. This is also the shadow completely disappearing. On the right, you can see a car below which there is a shadow, but the sun rays are falling vertically downwards. So what Iratus, so you see, if here, this is a very beautiful video of Carl Sagan. If you go to YouTube and write Carl Sagan's video of vanishing of the shadow, you will see this video. And I encourage all students to see this video. And this is a screenshot from Carl Sagan's video showing that the shadow will be of unequal length only if the earth is curved. If the earth was flat, then the shadows will be of equal length. But because the earth is curved, so therefore you will have shadows of unequal length. So in nearby Cyan in near Mediterranean, in the video created by Carl Sagan, he showed that around noontime on June 21, in a place near Cyan, the sun is directly above a deep well. So what is the physics of the experiment? You see, here is Cyan, the sun rays are falling vertically downwards, and so therefore it casts no shadow. In a city which is 800 kilometers from here, the sun rays are not falling vertically downwards, and so therefore there is a small shadow. And this is the city Cyan, this is the city Alexandria. So what he did was he measured the length of the shadow and therefore the angle theta. And once you know the angle theta and this arc length 800 kilometers, you can calculate the circumference of the earth. So the circumference of the earth will be 800 kilometers, and he measured theta to be 7.2 degrees. So 7.2 multiplied by 50 is 360. So he predicted that the earth is round and his circumference is about 40,000 kilometers, which is surprisingly very close to the correct answer. So the beauty of the experiment lies, Robert Crease writes, beauty of the experiment lies in the way it makes possible the discovery of a dimension of cosmic proportions by measuring the length of a tiny shadow. So by measuring the length of a tiny shadow on June 21, you can calculate the circumference of the earth. So this is an experiment that many students in India do. They go to a place in Ujjain or like that, watch the shadow, and at the same time, at the same instant, you find the length of the shadow in a place like Bombay or Chennai or Delhi. And by simple calculation, by knowing the distance between Ujjain and Chennai, you can calculate the circumference of the earth. The next experiment, the sixth experiment, is the Cavendish's torsion bar experiment, which determined the gravitational constant and weighed the world. He could determine, and this was in the year 1798. So as you know, this is Newton's laws of gravitation, which says that the force of attraction between two masses, m1 and m2, is proportional to the product of the masses, inversely proportional to the square of the distance, and the constant is the gravitational constant. To the above law, Feynman writes that to the above law, if we add the fact that if a force F acts on a body, then the acceleration will be given by A is equal to force by mass. So this law plus this law, if you have them, then Feynman says, there is a beautiful lecture that he has given on gravitation. And I would urge all students to listen to that beautiful messenger lecture on gravitation. You go to YouTube and write Feynman's messenger lecture on gravitation. And then he says that if I have these two laws, then I have said everything about the law of gravitation, except for the modifications made by Einstein in his general theory of relativity. So what Henry Cavendish did was an experiment like this. He had a massive ball and a small ball and suspended. And there's a very beautiful video on YouTube and it shows the attraction of the smaller ball to the bigger ball, and by measuring the twist, you can calculate the gravitational constant or the force of attraction that exists. So according to Professor Creeves, Cavendish in 1798 managed to carry out an extraordinary experiment whose precision could not be significantly bettered for 100 years. So you see, on the surface of the earth in 1 second, the ball falls by a distance of about 5 meters. And this was famous Galileo's experiment, that Galileo found out that on the surface of the earth, if you drop a ball from a height, then both the heavy ball and a small ball will take the same amount of time, and in 1 second, it will drop through a distance of about 15 feet or 5 meters. Now, please look at this calculation. So what Newton did was, he knew that the velocity of the moon, our moon, is about 1 kilometer per second. He knew the distance, which is about 400,000 kilometers. He knew that it goes through this, it's a circular orbit from the measurement of Tycho Brahe, and it takes about 27.3 days to make one full revolution. So the velocity of this is about 1 kilometer per second. So that the moon traverses a distance of about 1 kilometer in 1 second. This distance is 1 kilometer. But if the force of attraction was not there, from the earth, this is the earth, then it would have traversed in straight line. This is what Galileo had said. So it would have gone to the distance B, where AB is 1 kilometer. So therefore, because of the force of the earth, it passes through the distance, it traverses the distance BD. And if you do simple geometry, you will find that this is about 0.14 centimeter. So AD is about 1 kilometer, AB is 1 kilometer, and then using simple geometry, you calculate BD, it will come out to be 0.14 centimeter. So therefore, he said that the moon falls through a distance of 0.14 centimeter in 1 second. This is the calculation. A similar calculation was done by Newton. And since this distance is 400,000 kilometers, which is 60 times the radius of the earth, so he said that on the surface of the earth in 1 second, if the inverse square law is valid, it should fall through by a distance 0.14 centimeter into 60 into 60. That is 5 meters. So, and that he knew from Galileo's observation. And so therefore, he said that the force that exists between a falling apple and the earth is the same as the earth experiences, as the moon experiences with the earth. So thus Newton unified the gravitational force on the fall. This is his major contribution. Thus Newton unified the gravitational force on the falling apple with the force responsible for planetary motion. This is, according to Feynman, the greatest generalization achieved by the human mind. So he said that the force that exists between the falling apple and the earth is of the same type as between the moon and the earth, because the moon is about 60 times the radius of the earth. So the value of G will be 1/60th there. And so therefore, if this distance is 0.14, then on the earth, it will be 60 times 60 distance if the inverse square law is valid. So that is one of the greatest contribution of Isaac Newton. He generalized the law of gravitation. Feynman said that said this in his famous messenger lecture on gravitation. So you go to YouTube and write Feynman's messenger lecture on gravitation, you will get this. And it's a very beautiful lecture, and all of you, all students must listen to that. In the same messenger lecture on gravitation, Feynman also said, listen to this carefully. The law of gravitation is also used to calculate the prediction of planets' position, which have great utility for astrologists to publish their predictions and horoscopes in magazines. That is the strange world we live in. This is quoting Feynman. That all the advances in understanding used only to continue the nonsense which has existed for 2000 years. The next experiment, as you all know, the most beautiful experiment is Thomas Young's interference experiment, demonstrating the light was a wave. So Thomas Young did this experiment in the beginning of the 19th century. So he had two pinholes, not two slits. Remember, Thomas Young's experiment is not a double slit experiment. It's a double hole experiment. He allowed sunlight to pass through a filter, pass through two holes, and he observed interference fringes. And this can be explained only by assuming a wave theory, because if the particles were there, like I have adapted this diagram from Feynman lectures. So if a gun emits bullets, tiny bullets, then it will either pass through hole number 1 or pass through hole number 2. So if P1 is the intensity distribution when it passes through hole number 1, and P2 is the intensity distribution when it passes through hole number 2 and hole number 1 is closed, then when both holes are open, it will be just P1 plus P2. So this, because the bullets have to pass through either hole number 1 or hole number 2. On the other hand, if you have a wave source, then the waves emerging from here and here interfere. If one produces a displacement like this and the other is out of phase, then the resultant will be 0. And you will have an intensity pattern like this. So because he obtained interference pattern, he could say that light plus light could produce darkness. This is actually a quotation by Max Born. And as you all know, this we did read in high school, that the wavelength of light he calculated. This is beta is the fringe width, d is the distance between the two holes, and capital D is the distance between the slit and the holes and the screen. He calculated the wavelength, it was 0.5 of a micron, and he established the wave nature of light. Because before Thomas Young, people thought that light was indeed in the form of particles, and that was the Newton's corpuscular model of light. The wave theory was established only in 1801, after which the diffraction and polarization experiments were carried. Thomas Young was an exceptionally bright person, and there is a book which tells you about Thomas Young, the last man who knew everything. Thomas Young, he was a medical doctor, the anonymous polymath who proved Newton wrong, explained how we see, cured the sick, and deciphered the Rosetta Stone, among other feats of genius. So he was the great person who people say he knew almost everything. People say that in 20th century, the person who knew the entire physics, the last two persons were Richard Feynman and Lev Landau. Landau, the Russian physicist, they knew the entire physics. After that, no one knows the entire physics. The next experiment, the fourth experiment in the list, is Isaac Newton showed that a narrow beam of sunlight falling on a glass prism gets dispersed into various colors. This was his year of miracles. When Cambridge University closed down, he went back to his mother's home and did this experiment at his mother's home and near London. And so the year 1666-67 was Isaac Newton's Annus Mirabilis. Annus Mirabilis are Latin words meaning year of miracles. He was then just 23 years old. Because of an outbreak of plague in the United Kingdom, Trinity College in Cambridge, where he was teaching, closed, and he went back to his mother's home. There, in a room, in total isolation, Newton set up many experiments. In one of the experiments, he allowed a narrow pencil of sunlight to be incident on a glass prism, and he saw the white sunlight split into different colors. So before Isaac Newton, people thought that white light was the purest. Even today, many write that there are 7 pure colors: violet, vibgyor, violet, indigo, blue, green, yellow, orange, and red. That is incorrect. What Newton demonstrated was that all colors in between are also pure and fundamental. Let me skip this because I'm running short of time. So this is the Millikan's oil drop experiment. This is a beautiful experiment measuring the charge of the electron. This we do in BSc. Let me skip this. The second in the list experiment is Galileo's experiment on falling objects, that if 2 objects of mutual different weights are dropped from a height, both take the same amount of time. This happened in late 16th century. You see, Aristotle said that the heavy ball must fall faster. Aristotle said, and this was believed until Galileo, who said Newton's laws were still not discovered. So Galileo said that both the balls should fall at the same speed, and he demonstrated that by climbing on the. This is a story that he climbed the Tower of Pisa, and he dropped one heavy ball, one small ball, and he showed that both take the same amount of time in reaching the ground. So there is a very beautiful video which you must see. This is by video by Brian Cox. He took a very heavy object and a feather, and he allowed them to fall in vacuum. So he created a very big chamber, took the air out of it, and he showed that the heavy ball and the feather dropped with the same velocity. So if you go to YouTube and write down video by Brian Cox showing that a heavy object and a lightweight feather take the same amount of time, you will reach this website and see this beautiful 10-minute video. I wish I had the time to show you that. Then David Scott, the astronaut, he went to the moon and he dropped a hammer, a very heavy hammer, and a feather. And this is also on the YouTube. You must see that. And he allowed both of them to be dropped, and both took the same amount of time in dropping. And the most beautiful experiment. This is the last experiment, the double slit interference experiment with single electrons, which demonstrated the quantum interference of single electrons. This is a 20th century experiment. So, as you know, if a light beam passes through a single slit, it is done in any book on optics. You have the Fraunhofer diffraction pattern. It's a wave theory, simple wave theory. I is equal to I0 sine square beta by beta square, where beta is equal to pi b. B is the width of the slit. It's a long, narrow slit, and it produces the Fraunhofer diffraction pattern. Theta is the angle of diffraction, and lambda is the wavelength of light. Now, you want to solve the quantum mechanics. You want to find out what if an electron beam passes through. Then what will happen? Then you say that at t equal to 0, it passes through the slit. So you describe the electron by a wave function, which is 1 over square root of b. It passes through somewhere between the slit and 0 everywhere else. And if you solve the Schrödinger equation, then you will find, and I have done this in my optics book very carefully, in the latest edition of optics book, 7th edition of my optics book, very, very carefully. You take that wave function, solve the Schrödinger equation, and you find that the wave theory, the classical wave theory gives this expression. The Schrödinger equation gives this equation, that P of Px dPx is the probability of finding the x component of the momentum between Px and Px plus dPx. And that probability distribution is the same as the intensity distribution as predicted by the wave theory. It's a very beautiful analysis. Really, it is a very beautiful analysis. So according to quantum theory, the electron, the slit, imparts a momentum, and the slit undergoes a recoil. So there is a conservation of momentum. So a horizontal electron passes through. The source is very far away. So it is almost horizontal. Before it passes through the slit imparts a momentum in the x direction. And that probability distribution is the same as the intensity distribution. So quantum theory is probabilistic in nature. Classical physics is deterministic in nature. That's the qualitative difference between classical and quantum theory. Where will the electron land? You cannot say. But you can only predict the probability distribution. And beta is equal to the x component, the momentum, multiplied by b multiplied by 2h cross, which is the same as pi b sine theta by lambda. And this result is consistent with the uncertainty principle. So in quantum theory, uncertainty principle is contained in the Schrödinger equation. And Schrödinger equation cannot be derived. And Feynman says very beautifully, where did it come from? It came from the mind of Schrödinger. We next consider this is the final slide. Consider the double slit interference electron with single electrons. So you have as I told you before, you have particles coming out of a gun. It passes through slit number 1 or slit number 2. So it cannot pass through both the slits at once. It passes through slit number 1 or slit number 2. And so therefore, if P1 is the intensity distribution when slit number 1 is open, P2 is the intensity distribution when slit number 2 is open. When both holes are open, it is P1 plus P2. And the waves will predict an intensity distribution. So you do this experiment with a light wave, and this is given in any optics book, you get this intensity distribution. So this is the single slit diffraction pattern. It is given in any optics book, including my own book on optics. And you get this intensity distribution. And this is the 2-point interference pattern. If there are n slits, you have the grating spectrum. So this is beta is equal to pi b sine theta by lambda. And gamma is equal to pi d. D is the distance between the two slits. Now you do the quantum mechanics of it. So you say that the electron passes through either hole number 1. You assume a wave function where the electron passes through both the slits at once. This no one understands. That how does the electron pass through both the holes simultaneously? One single electron. This experiment has been done by single electron. That is, 1 electron goes there, say 2 electron goes there, 3 electron goes there. You would normally say that आधे वक्त यहाँ से जाएगा, आधे वक्त यहाँ से जाएगा. No, if you are not observing that, the electron is described by a wave function which is given by this. It passes through both the holes at once. How does it pass through both the holes at once? No one understands. And so therefore, as Feynman very beautifully says, that no one understands quantum mechanics. So if you solve the Schrödinger equation, which I have again done in my optics book, in my book on optics, then the probability of the electron getting an x is the vertical axis, is given by this expression multiplied by this expression, which is the same as the intensity distribution as you obtain by solving by using wave theory. थोड़ा detailed है, इसको करना है. And so this is the probability distribution as obtained by solving the Schrödinger equation. This is the intensity distribution as you get by using simple wave theory, as is done in almost all books on optics. So therefore, how do we explain this? You have an electron gun. Electron has a very tiny mass and a very tiny charge. So dekho, I know the mass of the electron. Electron was discovered by J.J. Thomson in 1897. I know the charge of the electron to 10 decimal places. It can be deflected by an electric field or a magnetic field. So I, on the back of my mind, मैं क्या सोचता हूँ उसको, एक tiny particle है. अच्छा, now I do this experiment. So what should I expect? The electron will either pass through slit number 1 or slit number 2. P1 is the intensity distribution when it passes through slit number 1. P2 is the intensity distribution when it passes through slit number 2. और जब दोनों slit खुले रहेंगे, so it will be P12 is equal to P1 plus P2. But when you observe this, you expect to this, but when you observe the interference pattern. And that quantum mechanics tells us that the electron passes through both the holes simultaneously. वो यहाँ भी है और वहाँ भी है. And it interferes with itself to produce this beautiful interference pattern. So this is the buildup of the interference pattern. This is the most beautiful experiment in physics. With 10 electrons, 100 electrons, 3,000 electrons, 20,000 electrons. And now when you have 1 million of electrons, slowly the interference pattern will build up. अगर 10 इलेक्ट्रॉन से तुमने एक्सपेरिमेंट किया तो यहां पर 10 स्पॉट्स आएंगे. वो कहां पर आएंगे पता नहीं. वेव थ्योरी will predict a pattern like this, very weak pattern, but a pattern like this. But quantum theory tells us that when you detect, you will detect a single electron and nothing else. And so electrons, Feynman says this in his very famous Feynman lectures, do not behave just like particles. They do not behave just like waves. Electrons in orbit are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification. Electrons behave exactly the same way as photons. This is Feynman's own words. So I think when he says that, I can safely say that, but this will require a further discussion. Maybe someday I'll do that. The two-slit experiment for electrons or for photons or for protons is a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. So if you do this single photon source with a beam splitter, so one photon, एक photon जा रहा है. तो अगर beam splitter है, तो तुम लोग क्या कहोगे? You will say that if there are 1,000 photons, 500 इधर जाएंगे, 500 इधर जाएंगे. That is a wrong answer. The correct answer is a single photon is described by a wave packet which is here as well as here. ये यहाँ भी है, ये यहाँ भी है. When you make a measurement, it collapses from being here and here to at either here or there. And the probability is half and half. So this is a very long experiment. It takes hours and hours when I explain this to my BSc students. But so you have a tunneling through the barrier if you have an incident wave packet, and then there is a part reflection, part transmission. The alpha particle यहाँ पर भी है, यहाँ पर भी है. But if you make a measurement, it collapses to being either here or there. This is the photograph of a young girl with 3,000 photons, and this is with 28 million photons, and slowly it is given by a probability distribution and so on. So the most fundamental theory, which is the quantum theory, in 3 years we will celebrate the 100 years of quantum theory. Now available is probabilistic in form and not deterministic. And so this is an astronomer wrote to Professor Kreis, seeing the two-slit experiment done is like watching a total solar eclipse for the first time. A primitive thrill passes through you and little hairs on your arms stand up. It is utterly arresting in the way masterpiece of art or sculpture is arresting. So I have tried to describe the 10 most beautiful experiments in science. Sorry. What is beautiful? any material object which can give us pleasure in the simple contemplation of its outward qualities without any direct and definite exertion of the intellect, I call in some way or in some degree beautiful. And in that sense, I think each experiment was truly beautiful. So there is this beautiful book by Robert Crease, The Prism and the Pendulum, which gives the history of the 10 experiments, of the 10 people responsible for these 10 experiments. What I have done in my book is given the physics that I have tried to describe here, and this is published by Viva Books. Thank you for it. Professor Sharma, I'm through.
Sir, we can hear you.
Thank you very much, sir, for a nice lecture. And I think everybody enjoyed this lecture. Being a student of biology, I understand very much very concept of physics. And ऐसा मुझे लगा कि मैं कहीं खो गया हूँ, जिससे कि इतने लेक्चर खत्म होने के बाद में भी मुझे लगा कि मैं ऐसे सुनता ही रहूं। मैं बहुत सौभाग्यशाली हूं कि आपका लेक्चर सुनने मुझे मिला। In spite of that, I invite any participant who asks any question and any query to Professor Ghatak sir. Then
ऐसा है अनिल कुमार जी, अभी थोड़ा देर हो गया है, मेरा टाइम भी तो वो ऐसा करते हैं कि किशन लाल जी का सुन लेते हैं, एंड फिर अगर कोई क्वेश्चन रहा तो ठीक है।
Sir, can we mail you the questions as well?
हाँ।
Thank you, sir.
Thank you very much.
Definitely, sir, please, sir.
Thank you very much, Professor Ghatak sir. Actually, the book which you have written, Graduate Books Optics, we have been studied with that book, and now we are teaching with that book.
अरे वाह,
that book is something which we must admire, sir. Thank you very
उसका
much.
जो 7th edition है ना, I don't want to advertise that book, उसमें ये जो last का experiment है ना, ये really it requires a lot of concentration, and I have been teaching this for the last 40 years, so so उसमें ये सारे experiment को मैंने बहुत carefully, बहुत अच्छी तरह से without committing any error समझाया है. And the double slit experiment, and I have learned it, so I will tell all of you. If you have any questions, listen first to the 2 Feynman lectures, one on gravitation and one on probability and uncertainty. Both are beautiful. I always tell my young students that we are all very fortunate that we have YouTube. And YouTube se to matlab you can listen to anyone on any subject, and it is a fascinating thing. And listening to the Feynman lectures, listening to the lecture, even you can hear what Einstein had said about E is equal to mc square. And so I would request all of you to, if you have any difficulty, because Feynman ka ye hai na, he was a complete physicist. He knew you see, that is the beauty of Feynman lectures. There is no error. There is no error. हमारी किताब में शायद एक आध एरर निकल जाए, लेकिन उसके किताब में कोई एरर नहीं है. तो read the Feynman lectures. The double slit experiment is beautifully discussed in volume 3. तो बहुत अच्छा रहेगा. चलो.
Thank you, sir. Thank you very much, sir. Now, let me introduce our chief guest, Professor Kishan Lal ji, former director NPL. The time when he was the director, we have been there in the laboratory, National Physical Laboratory, under the guidance of Professor R.G. Sharma. At that time, he was the deputy director of cryogenic division. And we heard a lot about Professor Kishan Lalji from Dr. R.G. Sharma. And I heard like this also, sir, you have taught many scientists solid state physics, and they were so fascinated and motivated everybody wants to go for solid state physics, particularly crystallography. Sir, we are very fortunate to have a chief guest today. Let me formally introduce. I am not exaggerating if I want to introduce Professor Kishan Lal ji. Actually, hours and hours are required. So I am going to introduce him very briefly so that we can save the time and utilize the time to listen him and his ideas. Professor Kishan Lal ji obtained his MSc in 1961, the time when even I was not born, from Meerut College, and that time this college was affiliated with Agra University. After a short period as lecturer, he worked in the solid state laboratory, Delhi. He joined the National Physical Laboratory, New Delhi, in the year 1963. At that time also I was not born, sir. He obtained his PhD degree in 1969 from Delhi University in solid state physics. He worked at the IBM Watson Research Center during the year 1971-72 and was visiting professor at the University of Tokyo, a technical university, and many more like that abroad university. He was also a visiting professor at IIT Delhi, Jamia Millia University, and he was appointed as director of National Physical Laboratory in the year 2000 and served till 2003. Presently, he is an honorary professor at Indian Institute of Technology, Kanpur. Also presently, he is editor-in-chief of the Proceedings of Indian National Science Academy. His expertise is in X-ray diffraction techniques, solid state physics, crystal growth, and many more. He has motivated many scientists to establish different laboratories, not only in NPL, to other parts of the country also. So without taking much time, sir, I invite you to kindly deliver the valedictory address. Professor Kishan Lal ji. Thank you very much, sir. Namaskar.
Thank you for inviting me. Also, this somewhat peculiar introduction. You forgot that I am also a former president of Indian National Science Academy. And you also do not know that there are about 90 such academies in the world. And we have an organization, IAP, for that. Presently, I am co-chairman for that, one of the two co-chairmen for that. That is one of my main duties. Also, one of the universities in Gurgaon has created a C.V. Raman chair, and I know I am a C.V. Raman chair professor at that university, but that is not important. Main thing is that now you are celebrating basically Raman effects discovery, celebrating the contributions of C.V. Raman. I want to tell you one instance. When I was director of NPL, we every year, even now, have directors conference. At that time, Professor Murli Manohar Joshi was our minister. He chaired that meeting. Suddenly, he started telling about one of our very, very, very important teachers, Professor Roop Kishore from Meerut, who was a direct student of C.V. Raman. So Professor Joshi said, what is a teacher and a student? Professor Roop Kishore, I learned a lot for him. For 2 months, I served also as a lecturer in physics in Meerut College. How experimental lab must be run. Professor Joshi said, that Raman Saab, because of Roop Kishore, twice he visited Meerut College. So once he visited when Professor Joshi was a student. So he said when Raman asked Roop Kishore, how many students you have in a master's? He said, sir, we have 15 seats and 2-3 छोड़ जाते हैं, about 13 people. तो मजा नहीं आएगा. उनका BSc, उसने कहा we have 10 section, hundreds of students. उनका चलो वहाँ चलते हैं. We interact with BSc students. Joshi ji said he interacted for 2 hours with the students, ask anything. वो रामन साहब थे. तो उन्होंने कहा कि तब से जोशी जी said कि मैं केमिस्ट्री पढ़ना चाहता था. I decided I will study physics, and he went to Allahabad and he did his masters and so on. This was because today we are celebrating C.V. Raman. Other thing which because Rutherford name came, and I had also the great privilege of being very close to Professor D.S. Kutari. He was so many things in India. So he told how he got associated with Rutherford. Actually, he was perhaps the only person who did his PhD at Cambridge with Rutherford. But that I will not today talk about it. I will talk about something which are important today. I'm not also will talk about some of my work. But what is important today, where we should be now going? We are only talking and talking and talking, not doing and doing. Show me something. That is important. तो मैं थोड़ा सा वो कोशिश करूँगा. तो मैं now I will share a screen with you. अब मेरा डेस्कटॉप अगर आ गया तो मैं कर लूँगा. तंग करता है तो नहीं करूँगा. डेस्कटॉप. मैं तो सोच रहा था डेस्कटॉप से हो जाएगा. Just suppose I bring this thing here. Will it accept? नहीं. अच्छा, file.
Sir, minimize the screen and then tap on the PPT. It will came on the screen.
अच्छा, इसको minimize करूं?
Yes,
Opening
sir.
कह रहा है. Opening
Sir,
हो रही
this
है.
is Chandan Jha.
Opening हो रही है.
जी.
अभी कह रहा है opening, तो let me hope it does so. हो गया.
Yes, sir. Now hit the PPT mode.
अच्छा, अब ये कितना बड़ा आएगा वो तो आप लोगों के ऊपर है. You are screen share. ठीक है. तो अभी मुझे थोड़ा सा तो IAP का इस वक्त 100, as I was saying, about 100 academies in the world. So I have great honor and privilege to be co-chairman of these, and of course with INSA, and also this KRM University has created a chair in the name of C.V. Raman. तो अब हम देखते हैं कि जो बेसिक मुझे चिंता है कि साइंस और टेक्नोलॉजी का
Sorry, sir, for interrupting.
और सोसाइटल डेवलपमेंट में
Krishan
बहुत
sir,
रोल. लेट मी
Krishan
सी
sir.
वेदर आई एम
Sir, actually,
तो नहीं हूँ.
sir, the slide is actually, somehow very,
Small.
small. So hit that play button you see on your screen.
ग्रीन वन
मैं
सर,
देखता हूँ.
प्लीज
ये
ग्रीन
बटन
वन पे
है
एक बार
भाई.
क्लिक कर दीजिए सर. हाँ, ओके.
Yes,
ठीक
sir.
है.
Yeah, it's much better, sir. Thank you.
अच्छा, आप सुन तो सकते हैं ना?
Yeah,
I am not
definitely, sir.
muted.
Definitely.
राइट. थैंक यू. तो इस वक्त आउटलाइन जो है कि एक तो इनोवेशन, सोसाइटल डेवलपमेंट में क्या चाहिए. दूसरा, इस वक्त नए एरियाज पर्टिकुलरली जिसमें यहाँ कोई चर्चा नहीं हुई और इंडिया के लिए क्रिटिकल है. अब नया जो सिस्टम है वो आर्टिफिशियल इंटेलिजेंस है, मशीन लैंग्वेज है. ये इतना ज़्यादा है इस वक्त इम्पोर्टेंट कि हम लोग पीछे रह जाएंगे इफ वी डोंट डू, एंड पर्टिकुलरली इन आवर universities and other institutions. Then I would personally, being an experimentalist, I would say there is a lot of need to put emphasis on experimental activity. हमारे यहाँ सबसे बीमारी क्या है कि हमें अगर समझ आ गया तो हम समझते हैं ठीक हो गया. समझ नहीं, आप यूज करके दिखा सकते हो. कोई ऑपरेटर्स है बना सकते हो. हमने सारी उम्र ऑपरेटर्स खुद बनाए. आप IBM का नाम ले रहे थे. आई बिल्ड इक्विपमेंट हेयर, समबडी केम फ्रॉम IBS, सॉ इट एंड गेव मी इनविटेशन. हमेशा ऐसा ही होता है. आप बना के देखो, देन थिंग्स विल चेंज. अच्छा, अब जो बेसिक देखते हैं कि भाई हमने जो शुरू में था इंडस्ट्रियल रेवोल्यूशन जो आया तो उसमें ये था कि भाई साइंस लीड्स टू टेक्नोलॉजी, टेक्नोलॉजी लीड्स टू प्रोडक्शन एंड देन ये कम्स प्रॉस्पेरिटी, STPP। अब जो उसी में पैरेलल में क्या आया, कोरिया, जापान, ये कंट्रीज, उन्होंने कहा भाई साइंस बाद में कर लेंगे, प्रोडक्शन लाओ, प्रोडक्शन विल लीड टू प्रॉस्पेरिटी। अब हमारे पास मुसीबत ये है कि हम समझते हैं हमें आता है, टिल यू मेक समथिंग, यू डेमोन्स्ट्रेट समथिंग, यू डोंट नो इट। इन लोगों ने उसमें मुझे जो पहली बार जापान बुलाया तो आई हैड मेड ए 3 crystal diffractometer, दे प्रोफेसर कोरा हैड मेड, तो ही invited me, मैंने कहा नहीं हमारा बेटर है, and I had to prove him in 2 weeks that ours is slightly better than that, and since then I had gone n number of times there। लेकिन मैं अपनी तारीफ नहीं कर रहा हूँ, मैं सिर्फ ये कहना चाहता हूँ, if we want to progress we have to have science leading to technology leading to production, only then prosperity will come। so latest technology बहुत इम्पोर्टेंट है, इसमें वेंडर्स भी चाहिए, सारा काम करना पड़ेगा। आप अगर एक आपका जरा सा अपरेटस हो जाए खराब, यूनिवर्सिटी चला नहीं सकती, वो फिर कुछ फायदा नहीं। वी हैव, आई एम बीइंग लिटिल रफ, पर ये हमें करना होगा। मैं दिखाऊंगा अभी कि एक मेरे पास कुछ नहीं था तो अभी रिसेंटली हमने क्या किया, हाउ टू प्रिपेयर ए क्रिस्टल्स मेड ए, और उस पर पेपर भी छापा। हमारे पास मशीन नहीं थी पुलिंग की, आई विल शो यू दैट। तो अब ये है कि जो स्टैंडर्ड्स, चूँकि मेट्रोलॉजी इन दिनों काफ़ी चेंज आया है, उसमें मेट्रोलॉजी अब वही नहीं है। पहले तो हम ये था कि हमने 7 यूनिट्स बना लिए और कहा कि 7 यूनिट्स का एक एक स्टैंडर्ड हमने अलग कर दिया और उसका इंफ्रास्ट्रक्चर वगैरह CIPM और BIPM से मिला लिया। इसका मैं थोड़ा सा और जिक्र करूं, जो शुरू के पायनियर्स थे उन लोगों ने डंकिर्क से लेके और बार्सिलोना तक वो 1/4 ऑफ द अर्थ का हिसाब से लगाया और लोग मीटर रॉड लेके चल गए वहां पर, और उन्होंने तब कहा कि इसको 10,000 मान लेते। मीटर की डेफिनेशन शुरू ऐसे हुई। दे आर वेरी वेरी डिटरमिन्ड पीपल हु डिड एक्चुअल एक्सपेरिमेंट। अब इसी स्टैंडर्ड्स का थोड़ा सा मैं जो हमारा ट्रेडिशनल है उसका भी दिखाऊंगा। लेकिन अब जो चैलेंज है, एक तो ये आर्टिफिशियल इंटेलिजेंस है, मशीन लैंग्वेज है, क्वांटम कंप्यूटेशन है। मैं बहुत खुश था, पीछे DST ने काफ़ी बड़ी मीटिंग की, आस्क्ड मी टू चेयर दैट, कि कैसे क्वांटम कंप्यूटेशन यहाँ लाई जाए। हमें तो यहाँ कर पाएंगे, थोड़ा कर पाएंगे, शायद बिल्कुल भी ना कर पाए, वही हमें काम आएगा। वट एवर यू कैन डू इन योर लेबोरेटरीज, वट एवर यू कैन डू इन योर सिस्टम यूनिवर्सिटी, दैट इज वट विल शो यू दिस। अब इसमें जो सबसे बड़ी चीज है ये कि मेट्रोलॉजी में अब सारे 7 बेस यूनिट है, उनकी डेफिनेशन बदल गई। नाउ यू डोंट डिपेंड अपॉन एनी आर्टिफैक्ट। अब वो आर्टिफैक्ट का जमाना खत्म हो गया। जितने फंडामेंटल कांस्टेंट हैं वो सारे मेजरमेंट में आ गए हैं। जैसे मास एक बड़ी मुसीबत थी, शायद टू मेक इट इंटरेस्टिंग आई में से NPL की ये ट्रेडिशन है, बीइंग ए कस्टोडियन ऑफ स्टैंडर्ड्स, जब भी नया डायरेक्टर आता है, पुराना डायरेक्टर उसको एक प्लेटिनम इरिडियम की मीटर रॉड और 1 किलोग्राम का आर्टिफैक्ट जो वेट है वो दे जाता है और वो ट्रांसफर होता है बड़ा फॉर्मली, क्योंकि उसमें 2-3 ताले वाले लगाने, महंगा भी है। और एवरी 4 years दिस किलोग्राम यूज टू गो टू पेरिस, हैड ए बाथ, क्योंकि इसकी सरफेस पे कुछ ना कुछ एड्जॉर्प्शन से वैल्यू बदलती। अब ये हो गया है कि हमने ये सारी इश्यूज खत्म कर दिए हैं। जितनी भी बेसिक मेजरमेंट की यूनिट्स हैं उनको फंडामेंटल कांस्टेंट से जोड़ दिया। ये उसमें मास वाज द मोस्ट डिफिकल्ट वन व्हिच हैज नाउ बीन डन, एंड आई विल से समथिंग अबाउट दिस। थोड़ा सा इसका हिस्ट्री भी बता देते हैं। अब एक में हमारे यहाँ अद्भुत है, हमारा, मैं अभी भी देख रहा था, ऋग्वेद में इसका जिक्र है। ये जो हमारे यहाँ एज ए प्रतिमान जो है स्टैंडर्ड क्या होगा, ये ऋग्वेद में भी आता है। आज मैं नहीं दिखाऊंगा, किसी दिन मौका लगा वो भी दिखा दूंगा। तो ये मनुस्मृति हालांकि बड़ी वो उसको मलाइंड है, ये किंग की ड्यूटी ये भी थी, तुलामान प्रतिमान सर्वम स्यात् सुलक्षितम और षट्सु षट्सु च मासेषु पुनरेव परीक्षा। वो 6 महीने के बाद दोबारा उसकी परीक्षा करेगा। राजा की क्या ड्यूटी है कि वेट्स और बैलेंसेस जो है नाप तोल के उसको 6 महीने में पक्का करेगा, और ये टाइम्स इमेमोरियल, लेकिन बीच में हम लोग खो गए। और इसी तरह ये कौटिल्य के अर्थशास्त्र में शुरू में दिया हुआ है कि इवन परमाणु को दिखाया कि 8 परमाणु रजा कण है। आप जिसको बिल्कुल दरवाजा बंद करके जो अगर लाइट ना लोगे कितने नाप सकते हो, उसके हिसाब से उन्होंने किया। इसमें वो भी है 4 बांस 24 गज अंगुल अष्ट प्रमाण ताऊ पर सुल्तान है मत चुके चौहान। अब पृथ्वीराज को वो डिस्क्राइब कैसे कर रहा है, 4 बांस 24 गज अंगुल अष्ट प्रमाण, उसके ऊपर है राजा मार तीर उसको। ये एक तरह से हमारे अंदर था, बट इन बिटवीन वी लॉस्ट दिस थिंग। इसको मैं आज नहीं ज्यादा चलूंगा। रत्ती मासा, मैं व्हेन आई वाज यंग इट वाज द थिंग। इजिप्ट में उन्होंने क्या किया कि लेंथ के लेके उन्होंने कहा भाई जो फेराओ जो रूलर है उसकी देख लो 4 आर्म की लेंथ ले लो मुट्ठी से, और उसकी ये घुटने तक ये डिस्टेंस, लेकिन ये चला नहीं। फिर इसके बाद फुट ऑफ द रूलर आया, उसको मैं छोड़ देता। लेकिन ये फ्रेंच साइंटिस्ट, मैंने कहा कि वो उन्होंने 10⁻⁷ ऑफ क्वाड्रेंट ऑफ द अर्थ, ये डंकिर्क और फ्रांस में और बार्सिलोना स्पेन में उन्होंने खुद से जाके नापा। ये उनकी कमाल थी। फिर वही शुरू में वो प्लेटिनम की रॉड वही मीटर बन गया। उसकी कहानी किसी दिन और सुनाऊंगा। उसको निकालने के लिए जब इसके 100 साल हुए थे, आई वॉज ऑल्सो एज डायरेक्टर, आई पार्टिसिपेटेड, एंड देयर वर अबाउट 30-40 Nobel laureates, and all of us were lining up to see all the meters and all the kilograms historical which they displayed on that evening. उसकी थोड़ी और भी कहानी है, वो ज़्यादा मैं नहीं करूँगा। कि शुरू में 16 कंट्रीज ने मिलकर यूरोप में ये ट्रीटी साइन की, उसमें यूएस भी शामिल था। फिर इंटरनेशनल ब्यूरो बना, फिर इंटरनेशनल सिस्टम ये साइंस बना, फिर मीटर की जो डेफिनेशन है, फिर 83 में आके इसको वेलोसिटी ऑफ लाइट से जोड़ दिया। उन्होंने कहा भाई वेलोसिटी ऑफ लाइट ले लो, ये फिक्स रहेगी। वेलोसिटी ऑफ लाइट से अब आर्टिफैक्ट से नहीं है। और लेकिन अब जो मैं जिस चीज को मैं लाना चाह रहा था, मेन चीज ये है कि करीब 2 साल पहले से, और 2 साल से भी कम है, 20 मई 2019, ये भी एक मेजर लैंडमार्क है। all these changes, all definitions have been changed globally. सारे दुनिया में अब जो ये बेस यूनिट्स हैं इनकी डेफिनेशन बदल गई है। सब यूनिट्स को फंडामेंटल कांस्टेंट से लिंक कर दिया गया, पहले सारे नहीं लिंक थे। इसको दिखाएंगे। जैसे 7 बेस यूनिट लेंथ है, मास है, टाइम है, इलेक्ट्रिक करंट है, टेम्परेचर है, ल्यूमिनेसेंस इंटेंसिटी, अमाउंट ऑफ सब्सटेंस है। पहले मुसीबत क्या थी कि आपने एक आध को तो हम कर लेते थे, अब सारी की सारी 7 यूनिट, जैसे फॉर एग्जांपल सेकंड है तो ये सीजियम का वो लेके आप अनपर्टन सीजियम 133 उसकी कहेंगे कि इतना सारे इसके ऑसिलेशंस हैं। जब हम इसको हर्ट्स में करें पर सेकंड, तो ये सेकंड की डेफिनेशन होगी। मीटर नाउ वेलोसिटी ऑफ लाइट के टर्म में हो गया। इसी तरह किलोग्राम वाज द मोस्ट डिफिकल्ट टू चेंज, इज द लास्ट वन टू बी चेंज, क्योंकि ये आर्टिफैक्ट इसको कैसे चेंज करें। नाउ वी हैव कम राउंड ग्लोबली टू फिक्स a numerical value of the Planck constant, which is 6.626 etc. 10 to the power -34. This is precise. इसमें कोई चेंज नहीं होगी। प्लैंक कांस्टेंट फिक्स हो गया, उसके डिपेंड उस पे ही जो है किलोग्राम अब डिफाइन किया जाएगा। इसी तरह केल्विन है, मोल है, कैंडेला है। ये पहले क्या था कि जैसे एम्पियर को आप मास और किलोग्राम और मीटर और सेकंड से कर लेते थे, एक एक दो दो को करते थे, लेकिन अब जमाना बदल गया है। आप किलोग्राम भी सब आपस में जुड़ गए। किलोग्राम का आप मीटर से भी है, सेकंड से भी है, कैंडेला से भी, यू कनेक्ट एवरीथिंग, बट डायरेक्टली इट इज लिंक्ड टू प्लैंक कांस्टेंट। मोल एवोगैड्रो नंबर। इसी तरह सबका आपने इलेक्ट्रिक करंट, एलिमेंटल चार्ज जो इलेक्ट्रॉन का, तो ये आने से फिर दूसरा एक और चीज है, हमें ये भी है कि भाई जो ये फिगरेटिव है, आपने नंबर बहुत सारे देने हैं, 10⁻24 इसकी भी डेफिनेशन है, योटा कहलाएगा। 10⁻⁻6 तो माइक्रो है, सब जानते हैं, मिली, माइक्रो, नैनो, पीको, और ये करते करते ये सब ऑफिशियली डिफाइंड है। तो अब जो भी मेजरमेंट है, इसमें एक चीज है जो साइंस है मेजरमेंट की, मेट्रोलॉजी स्टैंडर्ड जो मेंटेन करते हैं। फिर जो आपकी एक चीज है, हाउ विल यू कैलिब्रेट। आपने ये कहा कि मेरा ये सिस्टम है, मैं कैलिब्रेट करना चाहता हूँ। फिर आप ये भी चाहते हैं कि ये एक लैब नहीं कर सकती, आपको सैकड़ों लैब चाहिए, उनको एक्रेडिट करना है कि वो भी नापे, हम उसको मानेंगे, और जो गड़बड़ करे तो एनफोर्समेंट है। तो इसका BIPM वगैरह इंटरनेशनली कैसे जाते हैं कि वहां से प्राइमरी लैब, सेकेंडरी लैब, फिर यूजर्स इन साइंस एंड टेक्नोलॉजी, ये इसका नॉर्मल है। अब जो मुश्किल है कि जो आज का ज़माना है, उसमें हमारी सबसे बड़ा जो एक चैलेंज भी है, इंडिया के लिए बहुत ही चैलेंज है, कि अब जितनी भी डिवाइसेस हैं, जितने भी डिटेल्स हैं, वो फाइनली यू कम टू माइक्रो इलेक्ट्रॉनिक और नैनो इलेक्ट्रॉनिक डिवाइसेस और चिप्स एंड अदर डिवाइसेस। अब ये सबको बताने की जरूरत नहीं है। हर बार आप देखो तो वो मोबाइल फोन कहता है कि मेरी तो इतनी बढ़ गई है, कैपेसिटी बढ़ गई है, इवन दिस थिंग एंड सो ऑन। लेकिन ये याद रखना है कि 61 में व्हेन आई पास्ड आउट एज MSc, 4 transistors and 4 resistors were put on 1/2 inch chip of silicon। उसके ऊपर उन्होंने करके दिस चेंज होती, फेयर चाइल्ड कंपनी थी, इट डजंट एग्जिस्ट नाउ। तो उन्होंने फिर ये माइक्रो प्रोसेसर आए। आज जो है, मैं इस वक्त के माइक्रो प्रोसेसर मुझे भी नहीं पता है, बट आई नो everything now goes to atomic dimension. That is why you can put so many features in one device, so many features in one device. But question is, ये बनता कैसे? अब आप शुरू करते हो सिलिकॉन पाउडर से, you grow a crystal from the melt by mostly Chakralsky technique, sometimes by float zone. Then ये वूल बना, इसको काट लिया, फिर काट करके अब हमने ये वी हैव टू मेक श्योर कि ये रिप्रोड्यूस करें, हम वही प्रॉपर्टी बार बार आनी चाहिए। तो बार बार कैसे आएगी? फिजिकल और केमिकल पैरामीटर किसको करें? रिप्रोडक्शन प्रॉपर्टी और डिवाइस बनाना है, तब भी कैसे आएगी? तो 4 चीजें हमें इंपॉर्टेंट हैं। उसकी कंपोजिशन, उसमें मेन कंपोनेंट क्या है, प्योरिटी क्या है, स्ट्रक्चर क्या है, और परफेक्शन, डिवाइसेस। तो हाई रेजोल्यूशन, चूंकि दिस इज माय फील्ड, वी कैन नाउ शो सम बेसिक्स ऑन दिस व्हेन यू कैन इवन इमेज वन डिसलोकेशन। आप ये सिंपल है, ब्रैग लॉ है, लेकिन आप इसको रिफाइन करें कि मुझे इतना पैरेलल बीम लाना है। आई स्टिल क्लेम नोबडी हैज इंप्रूव्ड अपॉन द 5 crystal X-ray डिफ्रैक्टोमीटर डेवलप्ड बाय अस एट NPL। आप उसके पहले 2 क्रिस्टल से K-alpha-1, आमतौर पे K-alpha-1 K-alpha-2 सेपरेट नहीं होती। We take one, then take a fraction of that, diffract, and finally also we analyze this। 1-2 एप्लीकेशन में क्लियर हो जाएगा। तो ये NPL में काफी बड़ा है, करीब 2-3 मीटर है, वहां से एक्सरे सोर्स से फाइनल डिटेक्टर तक बहुत सारे काम इसने किए। उसका ये था कि अगर थियोरेटिकली देखें, ये मोस्ट ऑफ यू मे नॉट हैव सीन, वो डिफ्रैक्शन करते हैं 1 डिग्री आ गया, होना चाहिए 3-4 सेकंड, व्हाट वी डिड वाज 3.7 सेकंड। तो ये, और अगर और दूसरा डिफ्रैक्शन है जिसके कम है तो 1.7 सेकंड। तो बेसिक चीज है कि अगर आपके पास कोई क्रिस्टल है तो आप बता दोगे एमॉर्फस है, पॉलीक्रिस्टलाइन है। अगर सिंगल क्रिस्टल है तो क्या डिफेक्ट है, कैसे उनको रिमूव करें, और प्रॉपर्टीज को कैसे बदल सकते हैं। इसकी बहुत सारी टेक्निक है, वो मैं आज तो नहीं बताऊंगा, लेकिन कुछ एक आध चीज का बताऊंगा कि या तो बल्क क्रिस्टल या थिन फिल्म और सिंगल क्रिस्टल का सिस्टम। फिर एक है एपिटेक्शियल, आप वही क्रिस्टल को रिप्रोड्यूस करेंगे। या इवेल्युएशन ऑफ लॉन्ग टर्म स्टेबिलिटी ऑफ सिंगल क्रिस्टल डिवाइसेस। ये इतना नहीं करूँगा, जो हम लोगों ने एक जो बहुत जब डिटेल में गए तो लो एंगल बाउंड्रीज वर नोन कि वो कुछ मिनट की होंगी, यानी डिग्रीज में हो तो है ही नहीं सिंगल क्रिस्टल, मिनट्स में हो उन्होंने कहा थोड़ा खराब है, और लो एंगल बाउंड्री है पीपल थॉट ओनली इट शुड बी सेवरल मिनट्स, बट वी डिस्कवर्ड ए न्यू defect with very small low angle boundaries, then dislocation and so on. This is one of the crystals grown, क्योंकि उस वक्त इसकी बहुत थी थर्मल लो थर्मल ग्रेडियंट, एक मेथड हम लोगों ने निकाला जिसमें ग्रेडियंट इतना कम है पर उसको ग्रो करना बहुत मुश्किल था। तो इसमें अब क्या था कि हम लोगों ने वो जो लो एंगल बाउंड्री मिनट्स में थी, तो वी कुड सी ऑल्सो लो एंगल बाउंड्रीज हाफ ए मिनट 33 सेकेंड, और एक पीक अभी भी 7 सेकेंड का है। फिर इसकी फोटो लोगे, एक में पीक पे करोगे तो करीब करीब उतना इतना हिस्सा मिसिंग है, दूसरा आ जाए। इसी तरह से आप ये 32 सेकेंड 16 सेकेंड ये हमारे फील्ड का है, हमारे घर से निकली हुई, हर जगह इसका बहुत इम्पैक्ट आया है। या आप एक ही क्रिस्टल के अराउंड जाओ, कहीं कहीं है और कहीं कहीं नहीं है, लेकिन पिन पॉइंट कहाँ पर आती है। और इसकी थोड़ा सा और भी था इसमें, आप केमिकली क्या होता है। अब ये बहुत एक हमारा फेमस वो था शुरू में हमें भी, कि यहाँ डिसलोकेशन की इमेज डायरेक्टली दिखती है। ये लाइन एक शीट ऑफ मिसिंग एटम्स है। फिर इसको हम लोगों ने जैसे डायमंड किया, ये नेचुरल डायमंड क्रिस्टल है जिसमें सारी उसकी ग्रोथ की हिस्ट्री भी है और डिसलोकेशन भी है। अब लास्ट में थोड़ा सा बनाना चाहता हूँ कि एक्सरे का रिफ्लेक्शन क्या रखा है। अब मुश्किल ये है कि जो एक्सरे पे वी ऑल नो लॉज ऑफ रिफ्लेक्शन, ऑप्टिक्स में हमने सब पढ़ा है, लेकिन एक्सरे पे आके एक बड़ी अद्भुत चीज होती है। वन वेरी unusual thing happens, that refractive index becomes less than 1. It is most of the time we know, अगर आप कहें refractive index of glass, water 1.3, glass 1.5, but at X-rays, coming to X-rays, it is slightly less than 1. And this depends upon classical radius of electron, your wavelength and volume of the unit cell and so on. So what does it mean? If you now, there is a critical angle, if you now shine X-rays, then they can be bounced back. ये specular reflection आ जाएगा because the refractive index is slightly less than 1. And we worked out कि कितने refractive index में कितनी change आती है with each material. और मैं एक एक्सपेरिमेंट दिखाना चाहता हूँ जिसमें अब रिफ्लेक्शन से अगर आप देखें तो आप रिफ्लेक्शन देखते भी हो, और उसके ऊपर अगर कुछ और रेज हैं, ये हमारे लिए बहुत सेटिस्फाइंग है। वन ऑफ रिसेंट एक्सपेरिमेंट कि आप उस पे जो लेयर है उसके इमेज भी कर सकते हो, सिर्फ इमेज ही नहीं करते हो। ये जैसे एक्सप्लोरिंग बीम था और सिर्फ 10 नैनोमीटर थिक ऑक्साइड लेयर है, यू कैन इमेज, not only image, I will show you, you can also find out the composition. और वो भी बताएंगे कि ये अल्फा क्वार्ट्स है या बीटा क्वार्ट्स है, स्टिशोवाइट है, सिलिकॉन के जितने कंपाउंड हैं दे आर देयर एट सब माइक्रोन लेवल, एट ए वेरी वेरी थिन लेयर्स, जो उसके ऊपर नैनोमीटर्स पे आई टोल्ड यू ऑन दिस थिंग। अब मैं एक छोटा सा एक्सपेरिमेंट बताना चाह रहा हूँ। I am now connected with this KRM University. They created a chair in the name of C.V. Raman. और as I said, हम लोगों का कुछ लिंक है रामन साहब से। तो अब मेरे लिए एक बड़ी मुसीबत थी। Can I set up something there? They don't have money. So I set up a crystal growth system at NPL. हमने बड़े बड़े बनाए जिसमें कोई मोटर पुल नहीं करती है। अभी कुछ जिक्र आया था कि आप पानी का फ्लो से कुछ कर सकते। सो पहली बात तो ये है कि आई वांटेड टू यूज द लोकल मटेरियल इन अराउंड गुड़गांव। देयर आर लॉट ऑफ प्लेसेस, देयर आर लॉट ऑफ पॉटर्स। आई ऑलवेज वाज वेरी इम्प्रेस्ड, so I knew there is a lot of clay around it. So we took a clay and made a furnace. Furnace is here, and then we would grow a crystal out of this. But how do you pull? I have no motor for this. So I put a float here, connected the crystal ka jo holder hai, it is connected with a float here. And when I open the tap here, then this float goes down and crystal goes up. And even the referee was shocked beyond this thing. Without a motor, we could pull this thing. But we paid a crystal with very uniform diameter. This got published about a few months ago. So now we also want to use this for refining materials because there is a lot of waste. So can we convert waste into wealth? We have zone refining using basically the similar, and maybe next time I will show it. So to summarize the S&T and innovation, there is a lot to do for solving societal problems, and major new developments were also the new definitions of base units. Now all base units are connected with fundamental constants. Then modern devices and gadgets, I was saying, I hope I had chaired a meeting on quantum computers, hope something big will come out of such activities. Then resolution, high resolution diffraction and reflection experiments. And I also showed you innovative crystal growth system. I had good fortune of having very many very good my colleagues who worked with me at NPL, students, postdocs, most of them did PhD. Professor Verma, our friend, philosopher and guide, remained till his last breath connected. Whenever he felt little bored, little down, he said, "Nahi, Krishnalal, if you are there, I will come there, want to talk half an hour." So this. And other thing which we did, dedicated last paper to Steph Kapaneva, who actually was the Pope. She dragged me into crystallography. She became a professor at Sofia, but she did her PhD with Delhi University while working at NP. And last paper was devoted to me. अब ये मैं थोड़ा सा अपना इंडियन स्पिरिचुअल आई कांट हेल्प इट, ये मैं थोड़ा सा आपको एक आपकी महाभारत से दिखा रहा हूँ. ये बहुत ही एक फंडामेंटल है. इट इज ए डायलॉग बिटवीन उमा जी एंड शिवजी महाराज. तो शिवजी महाराज ने कहा कि मुझे तुम स्त्री धर्म के बारे में कुछ बताओ. पार्वती जी, आप इसके बारे में आपसे अच्छा कौन बताएगा? तो वो उसका जवाब क्या देती है, ना चाहे एक साध्यम दिव्य व सागर समेत. वो एड्रेस कर रही हैं होली रिवर्स को. पार्वती, उमा सेड, ओ ओशन बाउंड रिवर्स, आई डू नॉट सी इन दिस वर्ल्ड और इन हेवंस any knowledge which anyone has created on his own without collaboration of others. Therefore, I humbly seek your counsel. मुझे ये अच्छा इसलिए लगता है, हमें भी साइंस में अपने को याद रखना है. हमने बगैर दूसरों के सानिध्य से, बगैर दूसरों के मेल से हमने बहुत कुछ नहीं अचीव किया है. तो उमा पार्वती भी कह रही है, therefore I humbly seek your counsel. और ये अंत में है कि विज्ञानम आनंदम ब्रह्म. बृहद आरण्यक उपनिषद में है कि जो विज्ञान से आनंद मिलता है वही भगवान है. हमारे लिए तो that is Brahm itself. So with this, I thank you for your patient hearing. I hope I have conveyed something. Thank you very much.
Thank you very much, sir. Actually, what I have been thinking since long, out of about 140 crore Indian, we could produce only one Raman.
Yeah, ठीक है.
I am wondering about it and I could not find answer. But today, from your lecture, I got the answer. Because saying many things never solve the problem. The thing is that we have to do it. and not theoretically, experimentally.
करके दिखाओ.
करके दिखाओ, करके देखो और करके बताओ. तो आज मुझे आंसर मिल गया. आई एम रियली ग्रेटफुल टू यू सर and for your enlightened talk. I request Dean of Instruction Professor Rajesh Mishra ji to kindly propose a vote of thanks. Actually, because of this pandemic situation, we could not invite you, sir, in the campus itself at RI Ajmer, but definitely the time situation will permit us, we invite all of you in the campus of RI Ajmer, and I hope you all of you will consider my request at that time. So Professor Rajesh Mishra ji, I request you to kindly propose the vote of thanks, formal vote of thanks. Professor Rajesh Mishra.
Thank you, sir. On the behalf of NCERT as well as RI Ajmer, I extend my sincere thanks to our chief guest, Professor Krishna Lal ji, and guest of honor, Professor Ajay Ghatak ji. Professor Ajay Ghatak ji, for accepting our request and sparing their valuable time for us and grace this conference. Our both guests are stalwart of their field, and listen to them is a wonderful experience for us. I am also thankful to Professor S.B. Sharma, sir, for guiding and supporting to organizing this conference in a very short time. I am thankful to Professor Chaurasia, head DSM, and chairperson of this session. I am also thankful to Professor Nagen Singh ji, Dean of Research, and all the head of the departments of the institute, Professor R.B. Parikh sir, Professor Ayushman Goswami ji, for their valuable suggestion to organize this conference in such a nice manner. I am also thankful to our organizing secretaries, Dr. Rana Pratap and Dr. Ved Prakash ji, for making this conference a great success. At last, I am thankful to all faculty members and supporting staff of ICT and e-learning and others, viewers who are participating this conference for their support and dedication. So once again, I am very much thankful to all of you who make this conference a great success. Thank you. Thank you, sir.
And thank you very much, Dean sir. Now I request the chairperson of the next session, Head DEE, to kindly proceed for conducting the chair session. And in this regard, the next speaker is Professor C.K. Ghosh ji. So I request Professor Parikh to kindly introduce the Ghosh Sahab and request him to deliberate on the topic.
Thank you, sir. Respected chief guest, Professor Krishna Lal ji, guest of honor, Professor Ajay Ghatak ji, speaker of this session, Professor C.K. Ghosh Sahab, Dean of Instruction, Professor Rajesh Mishra ji, Dean of Research, Professor Nagendra Singh ji, all head of the department, all chair and co-chair rapporteurs of different sessions, and all my dear participants and students. I welcome you all in this 2 days national conference on emerging trends in physics and physics education. This session, we are having a keynote speaker, Professor C.K. Ghosh Sahab, Professor C.K. Ghosh has retired from Indira Gandhi National Open University, where he has held different positions such as Director of the Student Support Services, National Center for Innovations in Distance Education, and Regional Center of West Bengal and Sikkim. He has taught physics at Scottish Church College, Kolkata, and IGNOU. He completed his PhD from Calcutta University in tin solid film while working as a scholar of CSIR as Indian Association for the Cultivation of Science. He has authored and co-authors several books, 4 in the area of physics at undergraduate level, 1 on innovation in distance learning, and 6 on volumes of general knowledge. He has published more than 100 research publications in reputed national and international journals in the area of physics and mathematics education and open distance learning in the form of research papers, articles. Various articles have been edited by him, edited literature in national and international journal of repute. He has been holding membership of statutory body of different university. I will not take much time, and I may request Professor C.K. Ghosh to deliver his keynote address on postulates in physics. Thank you. Ghosh sir.
Thank you, Professor Parekh, for the kind introduction. Honorable Chairman, sir, Honorable Professor Sharma, Honorable Professor Kishan Lal, Professor Ajay Ghatak, and all the dignitaries present. It is a rare privilege on my part to be here and be a part of this occasion where stalwarts like Professor Ghatak and Professor Kishan Lal have spoken, and I'm really feeling a little hesitant to be sharing the dais virtually with them. In fact, the 2 very important takeaways which I could have derived from their lectures was that Professor Ghatak had listed 10 beautiful experiments, and the first experiment, which was 10th in his series, Foucault's pendulum, is about demonstrating that Earth rotates around the sun, and that is without looking at the cosmos. So that is definitely a path-breaking experiment, and also about Newton's unification, that the apple and the moon, they fall in the same manner towards the Earth. And Professor Kishan Lal had invited our attention to the fact, which I think is a bane in our system now, that a subject like physics is gradually getting relegated to a theoretical subject, and we are not at all keen to perform experiments. So very meticulously, he has pointed our attention towards recommendations of NEP 2020, and we are indeed grateful to the stalwarts for setting the tone of this conference, and I feel myself privileged and proud to be a part of it. In fact, when I was contacted by RIE Ajmer, I have a very close association. I had been there during the years 2018, 19, 20, and perhaps that was my last official visit before the pandemic. And I always enjoy the hospitality which I get there, and those were on different occasions I had been there. And I'll definitely look forward to occasions when we can have such meetings physically. So when I was contacted by Rana Pratap ji and Ved Prakash ji, I was told that the main target group for this conference will be physics teachers and maybe also students, and I should pick up something from their subject area, which is normally taught in the 10+2 syllabus or the up to class 10 curriculum. Now, let me share my screen first. Sorry. Just a minute, I always falter at this particular position.
Sir, one green button will be there, share screen. You have to click on that while opening the window, sir.
I know that I've done it number of times. Every time I falter when. Is it there now? Has
Yes,
it come?
Yes, sir. Yes, sir.
Yes, it has come.
Yes, sir. Now you can click on
Slideshow.
presentation, sir. Bas.
Yes, yes.
Then it will be.
Sorry for the loss of time. Now,
It's okay.
when they had contacted me, I remembered one occasion during my school days. While studying physics, particularly during the undergraduate classes, we come across several assumptions, postulates, approximations, models, hypotheses, lemmas, and so on and so forth. And one of our teachers, a very erudite teacher, but he was very particular about spelling out the assumptions and postulates. And my friend sitting by my side, I still remember him, will cut a joke and just push me and tell, of course, in a whispering manner, not aloud, that, well, making assumptions and telling postulates is his prerogative. How can we challenge them? So jokes apart, from that very time, I was thinking that how we start with assumptions or how we start with hypotheses, how we initiate a topic. And this is one particular area where the students have some doubt, some confusion. So first, let us ask, what is an assumption? An assumption is something which is accepted without proof, and they manifest themselves through models, approximations, and other forms such as hypotheses, axioms, postulates, lemmas, and so on. Now, these are necessary to get a structure, a mathematical structure, mostly in the form of mathematical abstraction. Like, suppose we are going to derive the Maxwellian law of distribution of velocities. We are going to derive the relation PV is equal to 1/3 mc square bar. So you need a starting point, like our constitution. So this constitution is a book where all the articles are framed. So those are starting point. Now, in order to frame that article, or in order to frame that series of articles, you had a constituent assembly. So you had to create that constituent assembly. And we don't go to question the authority of the constituent assembly. So this was the starting point, but that starting point, be it the creation of constituent assembly, or in case of physics, be it creation of the postulates, there must be some background, some kind of conjecture, some kind of experiences, some kind of empirical reasons to arrive there, which are not really proofs in the analytical sense of the term. So this I'm trying to explore, keeping myself restricted. I'll try to restrict myself to the +2 syllabus. Now, what are approximations? Just a minute. See, approximations have a different meaning. Like if we want to prove the famous equation alpha is equal to beta by 2 equal to gamma by 3 in thermal expansion, where alpha is the coefficient of linear expansion, beta is the coefficient of superficial expansion, and gamma is the coefficient of volume expansion. So we all know that we arrive at the formula for area at T degree temperature is equal to 1 plus beta T. And then we take a square of length L naught. So we say that L square is equal to L naught square into 1 plus alpha T whole square. And then when we perform this calculation, we write 1 plus 2 alpha T plus alpha square T square. So since this is of the order of 10 to the power of minus 6 and this is of the order of 10 to the power of minus 12, we say that nothing effectively gets added, and so we neglect this. So this is an approximation, and this approximation has a basis. Or when we write the equation, say GH, you are aware of the symbols, is equal to 1 plus H by R whole square. We are aware of this equation, that is G at a particular height H, and this is the value of G on the surface of Earth. And if you take the value of G on the surface of Earth to be equal to 10 meters per second square, and you go at a height of 1 kilometer, and R is roughly 6,400 kilometers. So if you calculate this, it comes to something like 9.99958, something like that, meter per second square. So this is very close to 10. So if we say that let us take the value of G to be 10, and we say for a motion taking place for a certain height, so 10, we will be doing problems at base for 10 meter, 1 meter, 5 meter, and so on. So if it remains almost that same for a stretch of 1 kilometer, so it will remain the same for a stretch of 1 meter, 10 meter, 5 meter, and so on. So these are approximations, and we have a tendency to use the words, by the way, and this is an axiom. So this is to sensitize you about an axiom, and this is a famous axiom about parallel lines, that through any point in plane, there is at most one straight line parallel to a given straight line. This is again a starting point. And we did not go to prove that. This is an axiom. But then we have a tendency to use these words interchangeably. Hypotheses, axioms, models, postulates, and so on. Now, I have separated out approximations from here because I have established that approximations can be arrived at analytically, as I have showed here. And even beyond that, you have famous approximations like WKB approximation, Wenzel-Cramer-Brillouin approximation in quantum mechanics, or say Born-Oppenheimer approximation. But more than that, suppose in quantum mechanics, we have three very fundamental problems like the square wave potential, harmonic oscillator, hydrogen atom. These are absolute problems. They can be solved absolutely. But once from hydrogen atom, you go to helium or even deuteron ground state, you have to use approximation. So approximations have a different role to play, and they govern our calculation, and they lead to different kind of solutions, and they have analytical basis. But once you come to the domain of hypothesis, models, and postulates, well, as I told you, there are subtle differences between these terms, and let us try to understand that. First, about hypothesis in the method of science. Hypothesis has a unique place in the method of science. What is the method of science? That you observe a phenomenon. Now, C.V. Raman had observed the blue of the ocean, and he questioned. And initially, he was provided the answer as was given by Lord Rayleigh, that he demonstrated why, or he explained why the sky is blue. And he said that the reflection of the sky in the ocean also makes it look blue. But Raman did not accept that. And he had questioned. He framed some hypothesis, he performed his tests, and then the rest is history. Now, in connection with any particular situation, you have to see a question. And in order to frame an answer to that question, you have to have a hypothesis which is testable. Testable does not necessarily mean that it should be experimentally testable. It can be tested in different ways. So you perform the test, And if the result of the test is positive, the hypothesis get accepted. Otherwise, an alternative hypothesis has to be framed and similar steps have to be followed. Now, in case of geometry, we prove by using the method of hypothesis. Say you have an isosceles triangle, and for an isosceles triangle, you know that if the two sides are equal, the two base angles are equal. This can be proved analytically. Now, what about the converse? The base angles are equal, then the sides will be equal. Now, how we do that? We frame a hypothesis that let AB not be equal to AC. And if AB is not equal to AC, one of them is longer than the other. Say AB is longer, and AB is actually, say, equal to AD. Then this angle ABD will be equal to angle ADB. But angle ADB is greater than angle ACB because of being the exterior angle of this triangle, and ACB is equal to angle ABC. It has been given, and so this part, which is a part of this, becomes equal to this, which is not possible. So we say that the hypothesis does not hold. So AC cannot be less than AB, so they are equal. So this is one way of handling the hypothesis. But this is for proving a particular thing. You frame a hypothesis. But here in the method of science, as I told you, you have to see a question, you have to frame a question. In order to get the answer, you have to frame a hypothesis. And then that hypothesis should be testable. So you test that hypothesis. And if the result is wrong, you go to alternate hypothesis and follow the same path. That is, you test it and you draw an inference from there. As it happened, and as I told you, that a hypothesis not necessarily be tested through an experiment. Let us consider two famous hypotheses, that is the Berzelius hypothesis and the Avogadro's hypothesis. That equal volumes of the same substance would contain the equal number of atoms, as was told by Berzelius, and that did not stand the test of time. That did not stand the test of Dalton's atomic theory, because it needed the atoms to be divisible. And then Avogadro came out with the alternate hypothesis that equal volumes of all gases under the same condition of temperature and pressure contain the same number of molecules. So that's how science rolls on and science develops. So that is the role of hypothesis. And then I'm coming to my point, that is postulates. Now, we have seen what is meant by an assumption. We have seen how approximations can be dealt analytically, and we have seen what is meant by an hypothesis. We have also seen an example of a lemma. The postulates are almost similar to that, but postulates are statements, a thing suggested or assumed as true as a basis for reasoning, discussion, or belief. And I have given 4 examples. I'll try to discuss the first 2 definitely, and if time permits, I'll also talk about at least the special theory of relativity, of course in brief, because as I told you that I'll try to restrict myself to the topics which are included in the 10+2 syllabus. And kinetic theory of gases, we say the model of kinetic theory of gases. Now, it becomes a model, and the edifices of the model are the postulates. So there are several postulates based on which the model develops. Same with Bohr's atomic theory. It is again a model based on several postulates. Same is the special theory of relativity based on several postulates. Same is the operator formalism in quantum mechanics based on several postulates. So let us see the kinetic theory of gases. We all know the basic postulate that the gas molecules are in the form of hard elastic spheres, and they are in a continuous state of collision. They are incessantly colliding with each other, and in course of the collision they change their path. They change their path in course of collision with themselves as well as with the walls of the content. Suppose I'm talking about a situation in Kolkata. Suppose you have seen the Brigade Parade Ground, where all the political, or I don't know whether you have seen or not seen, that several political meetings take place. Now suppose there is some commotion and the policeman will go and the crowd will run amok and they will start running helter-skelter. And from a tall building just opposite to the brigade parade ground, you are observing the motion of a particular person. He is trying to find a way out. He collides with another person, then he tries to find a way out in a different direction. So that is how the molecules would be moving. So I'm giving you a model. Now, why we say that they are in incessant motion? See, we Bengalis are rice eaters. And suppose I mix dal with rice, and when I go to test that, I find that, well, the salt added to the dal is not adequate. So I took a pinch of salt and I sprinkle on it, and I again remix it. Now, when the salt was in the sprinkle form, it was not moving. But you mix it, you use your fingers little bit, and within seconds, you find that the salty taste has spread throughout the dish. This is because of the fast motion of the molecule. You are applying perfume. You are doing that at a particular corner of a room, and I am standing at a different corner of the room, but immediately I'll get the smell of the sprinkling of the perfume. So these are bases. This is some sort of a basis of saying that they are moving incessantly. And in course of doing so, if things are moving so incessantly inside a chamber, they will definitely collide with each other. But the collisions are elastic collisions. So this is a stretch of imagination. And unless the collision is an elastic collision, perhaps you'll not be able to develop a mathematical model. So this is a kind of taking a calculated risk. Well, you cannot say with assurance that it would be an elastic collision. And then you say that the masses of these are point masses which are negligible. And then the most crucial thing, absence of intermolecular forces, that there is no intermolecular forces. And the point mass of negligible size means the volumes of the point masses are negligible. I have already said about themselves being in a state of continuous motion. They behave like hard elastic spheres, and we arrive at the relation PV is equal to RT, because the main relation which we prove is PV is equal to 1/3 MNC square bar, but the symbols have their usual meaning. And then from this we can arrive at PV is equal to RT. But when we consider the actual situation, now you see the deviation from the model. Intermolecular forces, as Professor Ghatak was talking about the probabilistic concept of the atom, probabilistic concept of the electron. And so the electron is definitely not sitting on the nucleus. The average position of the electron and the average position of the nucleus, they are different. So there will be some distance between them, say the distance is r, and they will interact. Two atoms will interact as two dipoles, because the charge on the say, since this is electrically neutral, the quantity of positive charge and the quantity of negative charge will be same, and the distance between them will be much smaller than the distance. You heard that the distance is of the order of 10 to the power of minus 15 meters. So this distance will be much smaller than the distances where its influence is being calculated. And two dipoles with moments mu1 and mu2, they have an intermolecular force of this order, r to the power of 6. Now this r to the power of 6 is crucial because this is square of r cube, so which is there in the volume, and that's why you have this additional term v square in pressure. And since it has a definite size, the value of volume is not v, but it is v minus v. So this is how this relation gets modified when we get the van der Waals equation. And this is a real gas equation, this is an ideal gas equation. And real gas equations are many, and in fact, van der Waals equation is not an ideal real gas equation. It is quite a poor real gas equation from the point of view of its resemblance with the critical constants, or point of view of its resemblance with the results of Andrew's experiment. But it gives the deviation by a single look, that is p changes to p plus a by v square, v changes to v minus v. And so you can understand the criticism, or you can understand the lacuna of the assumption of absence of intermolecular forces or the negligible size of the molecule. So this is what you get in the van der Waals equation. There are many equations. In fact, there is an equation in the name of Shah and Bosch, Meghnad Shah and Satyam Bosch. There is Dieterich equation, Bartlett's equation, Clausius's equation, which resembles the critical constants in a much better way. So this is the genesis of an assumption. This is the genesis of a model that they are tested. They are tested through our experiences, through experiments and so on. But the interesting feature is that this is a microscopic description. I hope you have observed this. This is a microscopic description. And from the microscopic description, microscopic descriptions cannot be felt by our senses. Microscopic descriptions cannot be felt by our senses, but pressure, volume, temperature can be felt by our senses. And from a microscopic description, you are coming to a macroscopic description. So that is the triumph of the model. And another basis is Brownian motion. Now, this observation was made by a botanist, but why does it find such an importance in the study of physics? One, because of the Einstein's equation. I'm not going to elaborate on that. And the other thing is that the kind of motion which was seen, I just now said that the microscopic state cannot be felt by your senses, but in a way, it gives you some essence about the micro world, which you observe, and then you apply them to create these postulates and arrive at some kind of a description which explains the macroscopic world to a great extent. And next, let me come to the atomic model. Atomic model, you all know, J.J. Thomson's model, Professor Ghatak had described it very adequately. I don't need to elaborate on that. But the situation was that the positive charge was distributed throughout the mass of the atom, and they mingled with the negative charge to make it electrically neutral. But then came that famous experiment by Rutherford, about which Professor Ghatak had explained. And so it led to the idea of nucleus, the central position of the nucleus, that there is a central core positive charge from where the alpha particles were scattering, and they even got scattered by 180 degrees. So we are all aware of that. Now this we call the planetary model of the atom, which came first from Rutherford's postulate, and then we got the master stroke of Niels Bohr. So the objection to Rutherford's model was that, okay, planetary model is fine because it's a central force, and as it happens in the case of the gravitational force, it's a central force. There you have attraction between the masses, and you have attraction between the charges. There also you have inverse square attraction. Here also you have inverse square attraction. So they are similar. So the planetary model was accepted, but what could not be accepted, that a rotating electron, because of its acceleration, would be radiating energy, and then will lose energy and will thus collapse into the nucleus, leading to the ultimate collapse of the atom. Now the master stroke came from Niels Bohr, that the orbits are stationary. The orbits are stationary, and it is standardized by this relation. That is, angular momentum is an integral multiple of h by 2 pi. And then when there is a transition from one energy level to another energy level, then the transition takes place by when it gets de-excited, the transition takes place with the release of an energy, and which can be explained through this relation E2 minus E1 is equal to h nu, where h is the Planck's constant. Now, why? Now these two postulates are based on two quantities. One is this angular momentum, and another is energy. Now this is again a kind of a basis, angular momentum and energy. The force is like this, 1 by 4 pi epsilon 0 q1 q2 by r square. This I should have written z is squared by r square r cap with a negative sign. This negative sign is because it's a force of attraction. Now this is of the form of a force like this, f of r cap, which is very much a central force. And in case of a central force, you know the torque will be equal to 0. r cross f will be equal to 0, which means that the angular momentum is conserved. Torque is 0 means the rate of change of angular momentum is 0. So L is equal to a constant. Now this is crucial. Bohr had to standardize the orbit, so he had to take a standard variable. He could not have taken linear momentum. He could not have taken linear velocity. He could not have taken angular velocity, but he took a quantity which is a conserved quantity. And then see the remarkable gift of the nature. See, he had to, in order to describe the stationary orbits. Now, if it is in the case of continuum, this discreteness is not there. So if there is a discreteness, this is the matter of conjecture. If there is a discreteness, it should be very small. And a very small quantity, which the small quantity which rules the microscopic world. Like if I say that the macroscopic world is ruled by the velocity of light, the microscopic world is ruled by h. So the standardization should come in terms of h. And now see the remarkable gift of the nature. This L and H have the same dimension of action. Both of them, both of them have the dimension kg meter square per second. Now, unless their dimensions were same, you could not have written this relation. I'm talking about simple mathematics. In order to have an equation, the two sides of the equation should be dimensionally same, if not anything else. So the first consideration was that it has to be a conserved quantity, and the second consideration was this dimensional consideration, by way of which the dimension of the two quantities separated by the equality sign are same, and it should be a small quantity. So all these things are fulfilled by the Planck's constant, and thereby this relation. And then if we come to the genesis of this relation, again, the first thing you have to appreciate that you are dealing with energy, the other conserved quantity. Had it not been a conserved quantity, you would not have found a place in the postulate. And then suppose a transition is taking place. Now, what is the guarantee that only one photon is coming? What I have written on the right hand side is the energy of a single photon. If there were 10 photons, if there were 100 photons, like this light is glowing on my head and a series of photons are coming all along. So why, but here this one is silent, this one is dormant. Why it is one photon? Now the first thing which might have occurred in his mind is that if it is not one, then the definition of frequency becomes infructuous. You cannot define frequency. This is an observable quantity. This frequency is an observable quantity. And then the striking feature is that Balmer series, that is the series of spectral lines which falls in the visible spectrum, was observed earlier, and that's how the Bohr's theory got effectively proved, got effectively demonstrated because of the Balmer series. But the first thing was to have a description of frequency, a meaningful description of frequency. And if you say that it can be n number of photons, then you cannot have a meaningful description of frequency. So this is like taking a calculated risk. You're saying that an electron knocks off a single photon, and so the energy is h. So these are the characteristics of the Bohr model, that for standardizing the orbits, two conserved quantities have been taken. The orbit being central, both angular momentum and energy are conserved quantities. Energy, you know that since it is a conservative force, since it is of the form of f of r, curl of the force is equal to 0, which shows that the line integral of the force across a closed path is equal to 0, and so the force is conservative. And since the force is conservative, the total energy is conserved. So we have taken two conserved quantities. And then the other gift of nature is that the dimensions of angular momentum and Planck's constant are one and the same. And during the process of de-excitation of an electron from one orbit to another, only one photon gets released. Had it been many, we could not have described what is meant by frequency. We could not have arrived at the definition of frequency. So let me quickly, do I have time, Chairman, sir? Or am I exceeding?
Sir, 5 5 more minutes you can take, sir.
5 minutes is fantastic. And in order to salute not only Albert Einstein, but other players of relativity, I should honor time, because that was the most crucial variable related with the special theory of relativity. That's why I asked about time. Now, there are two postulates of the special theory of relativity. Again, the laws of physics are same in all inertial frames. And by laws of physics, I mean laws of mechanics and laws of electromagnetism. And they are same in all inertial frames. No preferred inertial system exists. And the second postulate, the speed of light in free space has the same value in all inertial systems. So these are the two postulates which is there in all textbooks. But prior to that, the observer was described. And who is an observer? Who is an observer in the special theory of relativity? Now, in order to describe or define an observer, we consider a frame of reference. And by frame of reference, we mean a three-dimensional coordinate axis system. But then, say for a motion along a particular straight line, a one-dimensional frame coordinate system will also do. So let us make life simple. We take a one-dimensional coordinate system. An observer is someone who can measure a distance, who can measure time. So an observer is there with a scale which does not change its dimension anyway. In fact, we can remember what Professor Krishanlal was saying about the standardized dimension. But more importantly, he is measuring time. So is he moving with a clock? No. You have synchronized clocks. You have a set of synchronized clocks at every position of the frame of reference. So these are a set of synchronized clocks. So an observer is there with a scale for measurement and with a set of synchronized clocks. So this is the notion of an observer. And what we arrive at these consequences, that simultaneity is relative. Simultaneity is relative. Time interval is relative, the famous time dilation. Length is relative. But velocity of light is absolute, and it is the fundamental translational factor between space and time, the fourth dimension. These are the consequences. You must be aware of two very interesting limericks about the length contraction and time dilation. That there was a young man named Frisk whose fencing was exceedingly brisk. So fast was his action that the Fitzgerald contraction reduced his rapier into a disc. His sword was reduced into a disc due to length contraction. Or there was a lady named Miss Bright who could travel much faster than light. She departed one day on the Einsteinian way and came back on the previous night. So these are the two very important limericks. And what happens with the velocity of light being fundamental translational factor? Say, along with the three dimensions of x, y, and z, we wanted to include time. But that has to be an imaginary axis, because when you write the space-time distance square, it is x square plus y square plus z square, but you cannot just have t square, because they don't, again, for the same simple reason that x, y, z, and t don't have the same dimension. So in order to make them unidimensional, you have to measure time with some velocity. And what we do, we say this, that how far is Ajmer railway station from RIE, say 15 meter by taxi, 30 meter by bicycle, 45 minutes walk. So we are telling a distance in terms of a time, keeping in mind some velocity. So we are using velocity as a translational factor between space and time. So this velocity cannot be any velocity, but a velocity which is independent of the notion of source and observer, and such a velocity is the velocity of light. And so you get all the four dimensions. And so when you solve the relativistic quantum Schrödinger's equation, you not only get the three quantum numbers n, l, m, because S was already hovering around. This year is the centenary of Stern-Gerlach's experiment, which had established Gauss-Schmidt and Willenbeck's observation about spin. So spin is there, but how it is mathematically there? The corroboration takes place through the special theory of relativity. That is, the Schrödinger's equation is no longer a 3-dimensional equation, but it's a 4-dimensional equation considering the 4th dimension time. So quickly, let me sum up with the takeaways that it is always necessary to create a structure, a sort of mathematical abstraction using assumptions, models, hypotheses, postulates, and approximations. The words assumptions, models, postulates, and approximations should not be used interchangeably. Postulates cannot be proved analytically, but the basis of an approximation can be established analytically. I have showed that. Approximation methods are used for solutions of many crucial problems in physics. Postulates are in a way conjectural. They are based on experimental observations and evidences. So had my friend been there, I would have told him that it's not really the prerogative of the sir who was saying that I'll assume this, I'll assume that. It has basis and these are conjectural. And most importantly, they have by and large stood the test of time. So thank you very much for a very, very patient hearing.
Let me thank to Professor C.K. Ghosh sir for his nice presentation regarding the topic. He emphasizes various aspects related to day-to-day life situations based on different experiments. And while studying physics, what are the things which are very much essential and need attention? What are the role of postulates, basis of different themes based on reasoning, discussion like kinetic theory, atomic model, Bohr's model, and day-to-day life observations in different aspects. His lecture not only beneficial to physics or physics education person, but for chemistry person also, that was very much useful. So on my behalf and from institute side, I must say thanks to Professor C.K. Ghosh sir for delivering this nice lecture. Thank you, sir. If anything, Principal Sir S.V. Sharma sir want to share his experience within 1 or 2 minutes, then sir, please.
Thank you very much, Professor Ghosh sir. Because of the constraint of the time, I do not want to say anything. And I request you, Professor Parikh Saab, kindly organize the session in such a way that we will be able to accommodate our all paper presenters. So let us go ahead without taking much time. And time actually you can manage in such a way. Let us provide 5 to 6 or 7 minutes to each presenter and followed by 2 to 3 minutes for discussion if required at all. So let us go ahead.
Okay.
Thank you very much.
Thank you, sir. Thank you,
Ghosh
sir,
Thank you
for your presentation and for your presence in this 2 days conference on physics and physics education. Now we will start the participation or presentation from our participants. The first in this is Suresh Bhatt. He is a vice principal and his topic is presentation Artificial Intelligence Aided Physics Teaching, an experimental study on the development of artificial intelligence in teaching physics. So as told by Principal Sir, Professor S.V. Sharma Sir, that you have to be very, very brief and you have to present your topic related to what is the main problem or main objective of this particular paper or article, and what you have done and what are the conclusion based on this your article. I request rapporteurs for this session. I think Dr. Seema Rajput, she is here.
Yes, sir. Yes, sir. I am here.
And Dr. Ritu Sharma. Dr. Ritu Sharma. Okay, Seema ji, you have to take care.
Yes, sir.
So,
yes, sir.
First, Suresh Bhatt.
Yes, sir.
You can start
Namaste,
your
sir.
presentation. Yeah.
Namaste, sir. Am I audible to everybody?
Yes.
Yes, you are very much audible.
Okay, sir. Namaste. Respected Honorable Principal Professor S.V. Sharma sir, and all the professors, scientists, and eminent speakers, professors like C.K. Ghosh sir, Chairperson sir, and many heads of DSM, RIE faculty. RIE is like my mother because I studied in RIE, and all the like Dr. Seema ma'am and Dr. Ritu Sharma ma'am, Dr. Professor Krishnalal sir, Honorable Ajay Ghatak sir, Professor sir. So today I want to discuss about my paper, that is the topic is artificial intelligence aided physics teaching. So it is an experimental study on the development of artificial intelligence in teaching physics at the school level. So I would like to share the screen. Can I, sir?
Yeah.
Yes. I am the vice principal as well as I am a CBSE resource person. I conduct various workshops. And I also presented the paper in RI Ajmer in the previous session. Sir, is it visible? Whether the screen is visible?
Yes.
Can I go ahead?
Yes.
Yes. So it is basically, we all know that artificial intelligence is taking its baby step. We all know that, you know, Android devices have created a big mania, and you know, at the time of pandemic also, you know, hello, am I audible?
You are very much audible. Please go ahead.
Yes, sir. Yes, sir. Okay. So the artificial intelligence is going to make a big leap. I mean, you know, we can integrate artificial intelligence in physics teaching as well. So there are two things. One is artificial intelligence, another is robotics. So many are confused with the robotics and artificial intelligence. Actually, artificial intelligence is entirely different compared to robotics. In the case of robotics, actually, you know, the pre-decided programs will be fed to the device and that will do the work. But in artificial intelligence, it is a device which is very much learning like a student. Okay, and also it can be a teaching learning aid as well. So a machine learns what are the things that are possible, that is one side, and how artificial intelligence can study along with the student, and how it can be a competitor or a friend or a co-learner along with the student, along with the high school student. How is it possible? So I just thought about it and I wanted to do a small paper on that. So that's what I'm going to present before you all. So we all know, of course, how amazing the progress has been in AI in recent years. Nowadays, in all engineering colleges, the first course is artificial intelligence. So all the other things like civil engineering and rest all the field, like, you know, electrical, electronic engineering and all, they keep at the end, because, you know, one day really this AI is going to do a big difference in our life. That is especially in learning physics. Okay, so machine learning, if it is possible, if a machine starts learning and if machine is going to help us in learning physics, what are the difference it can make? So my objectives of my study are here. I'm just going to read out that. So to study the impact of artificial intelligence in the field of teaching and learning physics, to compare AI aided teaching with the traditional method of teaching physics. Because now we are all doing lecture method or the demonstration method, or you know, there are many methods, concept attainment, many models of teaching are there. But if AI comes into the physics teaching, what impact it can make on the student? To facilitate children to learn physics with the help of artificial intelligence, to amalgam the AI into real life experiences. Why I am telling about real life experience is that, suppose if I want to travel from Ajmer to New Delhi, and if I ask a student to calculate, he will just use a simple formula, speed is equal to distance by time or displacement by time, and he will calculate the speed or time, whatever we ask for. But in the real time, if you observe, we have Google Map. Actually, this Google Map is a AI, that is artificial intelligence. It's a real-time processor. In the sense, see, there are many constraints. Constraints like, one is the factors like, see, now traffic is a big, making a nuisance also. So, and other things like, obstacles on the way. So when a student is asked by a teacher about this, so the student in the present, that is in the 21st century, surely will think of Google Map. Google Map is actually a AI aided. AI aided in the sense it will give real-time calculations. So when, as a physics teacher, am I considering the constraints like traffic or other constraints like barricades, or am I actually calculating the displacement and distance? So what is happening?
1 minute more.
Yes, sir. Okay. So to encourage self-discovery method and to discourage, the classroom chalk and talk method. So here, what I have done is, you can see the picture. I am asking the students to do, in the Atal Tinkering Lab, I am asking them to do the project. Okay. Next slide. In the next slide, I have asked a few questions for the students, but I have initially I have divided the student into experimental group and experimental group and control group. So for the experimental group, I provided the AI assistant like a navigation, chartboard, speech recognition, text edition, autocorrect, face recognition apps. And for the traditional group, I provided just textbooks of physics and every material I provided, but they are all traditional tools. For the other tool, I provided AI.
Please go to result.
Yes, sir. Yes, sir. Yes, sir. Okay, then in the result, I have observed that, AI students, those I divided as AI, they were able to calculate accurately the distances. So for example, like 387 kilometers in 6 hours, 40 minutes. But today, when I take at different time intervals, the distances will vary and the time also will vary because of the constraints. So we have to understand the real time calculation as well as the traditional method of calculation. Now, when I asked a student about face recognition and the what kind of goggle students must wear, of what power, students was able to do with AI more accurately compared to the traditional method of doctors doing. So, and also GeoGebra, use of GeoGebra in calculating the voltage versus time graph. All that they were able to do with the AI age, which was much helpful for the student.
Thank you, Suresh. Thank you.
Yeah, implications of my study.
Your time is over, Suresh.
Yes.
Suresh, let me explain you that your time is over. You have already taken 7 to 8 minutes.
Yes, sir.
So please sum up within 30 seconds.
Okay. So implications of my study are artificial intelligence aided physics learning will come in the future days. So we have to be prepared. We should gear up because our students will take over the teachers and professors. So we have to be precise in calculations and we should be able to look at all the constraints and understand physics in a much better way. And also artificial intelligence will definitely cause the workforce to evolve. The job loss may be there in the future, but the job loss should be seen as a great threat to the humanity. But positive side is AI can create thousands of new jobs for our students in the future. So how we have to amalgam AI into physics teaching, we should learn. So it's taking a baby step, but in the next generation, surely in the 21st century, the collaboration should be there with AI. AI will learn along with the student will learn along with the AI. So we have to be very careful, as well as we should do a lot of research in this field and we should evolve this system.
Thank you.
So
thank you, sir. Thank you.
Yes.
Thank you.
Thank you, professors. Yes.
Is there any question? Okay. So shall we move next? Next is Dr. Smita Sharma. Dr. Smita Sharma.
Good morning, sir.
Yeah, you have to present on virtual experiments of physics using Scilab. So your time will be again.
Okay, I'll stick to time, sir.
Yeah, thank you. Sureshji, please, you just stop your screen sharing.
Yes, sir. Yes. Yeah. Okay. Yes.
Madam, please continue.
Sir, I'm sharing my screen.
Yeah. Has it been done? Yes. Okay.
Okay, good morning to you all. I am Dr. Smita Sharma, and today the title of my presentation is Virtual Experiments of Physics Using Scilab. So as we know that experimental observed facts in physics are generally explained through some theoretical concepts. Some of these theories can be calculated and are easy to verify. But some of the theories have complex calculations. As such, students are generally shown the end results directly by graph or final values. So here we have tried to design virtual experiments that explain these theoretical concepts by writing simple programs. All these have been done using Scilab. Now, what is Scilab? Scilab is an open source scientific and numerical computation software which is available under Windows, Linux, and Mac OS operating systems, and it is free to download. It can be downloaded at the following address. So everybody can use it. So what we have done, we have taken the idea of Sir Richard Feynman that what I cannot compute, I do not understand. For that, here we have designed a simple virtual experiment regarding linear harmonic oscillator, where a student is able to study the variation produced in the oscillations when different parameters like mass, spring constants are varied, and damping is introduced. By viewing the results, he can interpret them and verify them with the results given in his textbooks. So how we have done this? Before doing this any experiment, it is always required to develop for a student to develop the understanding of theoretical concepts and to know the clarity, get the clarity of what to observe. So for that, in a linear harmonic oscillator, we know force is equals to minus kx, and by writing it in differential equation form, we get this equation. D square x upon dt square is equals to minus k by m x. This so whatever variations that a student is required to observe can be observed by solving this differential equation. This we have solved with the help of Scilab software, where a command OD is provided, and we have written very simple and small program here as shown here. Here the differential equation is depicted by a function, and also the values of k and m are randomly taken for student to observe the result. When such a program is run, the student is able to observe the variation clearly by varying k when mass is kept constant, and by varying m when k is kept constant. He is also able to calculate the time period and observe the result. So he at once gets the idea what is being done here. He can further explore this by using the damped linear harmonic oscillator by simply adding an additional term as described in the textbooks. So here in simply by using the same program and adding this additional term, he gets a damped linear harmonic oscillator. And as he studies in damped linear harmonic oscillator case, there are 3 different cases. These are also observed easily, as I'll show in next slide. So here, when student varies the damping from 0.1 to 0.9, he can clearly observe the variation in the oscillations as shown in the slide. He can also observe the different 3 cases that were given in the theory. Clearly, he can see that when the ratio k by m is very less than u by m, the motion is oscillatory with decreasing amplitude. Then he can observe the critical damped case. Also, when over damped case is there, where k by m is very much less than u by m, we can say that motion is no longer oscillatory. So here in this small experiment, what student learns? he develops an understanding of theoretical concepts and gets clarity of what to observe. He learns to present them in form of a program, and he is able to observe the variation produced in oscillations due to different variation in different parameters, and he is able to interpret the result, and he can also verify them with the textbook, with the results that are already present in the textbook. So he is able to understand the theoretical concept and in an easy manner. This was one of the experiments. Many more experiments can be designed in such a way to get a more theoretical understanding. Thank you.
कौन है ये वाइस चांसलर है।
So, sir, I have completed my.
Thank you, Dr. Smita. Is there any question?
So one question is there.
Yeah, please. Yes, you can ask question. Sabir ji, you want to ask some question?
Yes, sir. Yes, sir.
Yeah, you ask.
Yeah, Dr. Sunita, you have shown that in this damped harmonic oscillator that you have calculated through this psi lab, you have shown that when you vary the mass, there is a variation in time period. But normally we teach that it's independent of mass. Time period is independent of mass.
I'm sorry, sir. I didn't get you. What you are saying?
In one of your slide, you have shown the calculation of psi lab that when you vary the mass, there is variation in time period. Okay.
Yes. Not for damped harmonic oscillator, I have taken simple harmonic oscillator.
Okay.
I have not shown for damped harmonic oscillator. I have this time period. I have only shown for simple harmonic oscillator undamped case.
Okay, but in also simple harmonic case, it is also independent of mass.
No, this I have taken a simple undamped case. I am not taking that T is equals to 2 pi under root L by G. Simple harmonic oscillator I am not taking. I have taken T is equals to 2 pi under root M by K.
Okay, 2 pi root under M by K.
In that case, I am discussing.
Okay.
I was not discussing the simple
Thank you.
pendulum experiment.
Thank you.
Thank you,
both of you, Sabir ji and Smita ji. Now, next presentation is on ICT in support of physics education. Dr. V. Gurinder Rao from.
Hello.
Yes, sir.
Professor Parekh ji. Sorry, actually, we have with us Professor Anand Kumar Tyagi ji, Vice Chancellor, Mahatma Gandhi Vidyapeeth, Varanasi. He is with us. I request him, please say some blessing words to our friends who are connected with us right now. And I know you are extremely busy and you have meeting and many more things to conduct. That is why if you feel you can share your blessing words to our participant. Chairman Professor Parekh ji, will you allow?
Namaskar, sir.
Yes, sir. Yes.
Namaskar. Am I audible?
Yes, sir.
Yes, sir. In fact, Dr. Sharma invited me, but I was given an assignment tomorrow, that is on Monday. But somehow we are having some engagements on Monday because Honorable Prime Minister is coming today and Honorable Minister of Education will be here tomorrow. So I will be busy. So I thought that at least I should be part of this wonderful conference. That's why I opted to come to the conference today itself. It is really very nice that RIE is arranging this conference and that also on physics education. As we all know that physics education is such an important issue that it has attracted attention of almost all engineering, social sciences, and science education disciplines. Because physics is such a subject where people feel that probably it's very difficult. It's a dry subject and probably we may not be able to understand it. But this myth, we all, the physics teachers, have to join hands and we have to remove this myth that physics education is basically the most interesting aspects of the entire education scenario. Because whatever we observe, whatever we see, whatever physical phenomena we see around us, we should basically try to analyze those things. And once we analyze, then we reach at certain inferences, and those inferences basically makes the concepts of basic physics. So that we have to basically tell almost to everybody. And one more important thing, that without physics, we cannot even think of any branch, because physics is basically dealing with the characteristics of all physical objects. Or unless or otherwise we completely characterize the physical objects, how we can interact with them. And in whatever branch, whatever discipline, whatever subject we are dealing with, you have to basically make an interaction, whether it is a living object or it is a non-living object. So everywhere you have to essentially interact with those things. And this interaction is possible only and only if you understand each and everything about them. So that's how I usually say this thing almost to everybody, even to social scientists, that at least some basic components, basic knowledge of physics is essential if you really want to have some knowledge. So that is what is the basic thing. Probably we should spread everywhere, since we all are physics teachers and we are involved either in teaching the physics or we are involved in doing some research on physics. So it becomes our holy and pious duty that we should spread this message to the entire education fraternity. The another challenge which I see before the physics teacher says that usually in physics, we have to primarily depend. Am I audible? Yeah, we have to primarily depend on the instruments and techniques, and we have to basically illustrate all those things, whatever we observe. Then and then it will be acceptable by our students. So that's how the physics is entirely different from rest of the knowledge disciplines. And here we have to be very careful, because the nature of the knowledge is being changing. Earlier, the knowledge was confined only to the classroom, but now the knowledge has gone out of the classroom. And once knowledge is, floating in air in the form of Google or in the form of various platforms which are disseminating knowledge to the learners, the role of the teachers has got changed. And more so, if it is a physics teacher, the role is entirely changed. We have to basically take help of some tools of education. We have to design our, some simulations or certain things which are available online, because it's always not possible that everybody will go to the physics lab and perform the experiment. But if you want to tell them about the principle, then unless or otherwise you are having simulations, you may not be able to attract these students. So in the change scenario where technology is at boom and the knowledge has gone out of the classroom, the role of physics teacher is, the need of the hour. It has to be modified, and accordingly we have to change ourselves. And in this regard, I always say that please, at least if you cannot even design the simulations, you can record the experiments in your laboratory with some good quality students, and then you can put those clippings on various platforms. So at least the students can see those things, that this is how this very particular principle of physical sciences is being depicted. So that is the alternative way, if you are not able to, because everybody cannot be expert in simulation and other things. So at least video making is a very efficient tool where you can record those experiments, put on various platforms and let the students see them. At least they will be having a glimpse in that as to how the principles can be depicted experimentally. And the third important thing which I would like to share is that we have to basically make everybody feel, every institution feel, because it is RIE, and you are addressing various learning avenues, various learning universities, colleges, and everybody. And you are also involved in teachers training. So somehow we have to tell each and every university, each and every college that we have to make the training need analysis for our physics teachers, and not only physics teachers, in general, we have to make the training need analysis. And accordingly, we have to design the modules for teachers training. And those modules, they can be aired online, or we can even, if at all possible, we can even arrange physical training to the teachers. So that was the third thing I was feeling, that probably because most of the people who are here in this conference, they are related with the teachers training also. So this suggestion probably will be quite helpful for the teaching fraternity. Besides this thing, I am really grateful to Professor Sharma that he has invited me for this conference. At the same time, I was seeing the list of experts, those who joined this morning. It was really very nice gathering today we had. And all the people, those who have worked on materials, advanced materials, and contributed a lot to the cause of physics, they were there on this platform today. And I feel that their presence will certainly make us feel that we still have a role to play, and especially the teachers in the changed technological scenario have to play a vital role. And of course, this dynamism has to be understood, and we have to keep on changing our role accordingly as per the need of as per the societal needs, as per the relevance of the technology available. And moreover, we have to design our curriculum, we have to design the pedagogy, we have to design the syllabi, and all other things depending on the requirements of various disciplines. One more important thing, which of course is the need of the hour, that we should make arrangements of teaching the physics to the non-physics disciplines also, because that is the need of the hour. Even for the social scientists or even for the law people, we have to design some basic courses on physics so that at least they can start understanding this world. And if they will start understanding the world, its physical treasure and other things, then probably they will be able to utilize their knowledge in a better fashion. With these words, I stop over here. I want to thank everybody who joined on this platform. And I feel that the conference will be resulted into nice deliberations and will give certain useful recommendations for RIE, for the teaching fraternity at all, and especially to the physics teachers. Thanks, everybody.
Thank you. Thank you, sir. Thank you.
Thank you very much, sir. You have spared your valuable time in spite of the fact you are extremely busy. And from the bottom of my heart, I'm really grateful and express my thanks to you. And formally, I request chairman of this session, Professor Parikh, to kindly propose the vote of thanks to our chief guest. Of course, validity session, but we are having him a day before validity. So, Professor Parikh.
Thank you, sir. Thank you, Professor Tyagi sir, for his nice talk in the session and discuss the issues related to today's concern about the physics and physics education and how we have to move keeping in the present situation. Once again, thank you, sir. So we will move further. ICT in support of physics education, Dr. V. Gundu Rao. Are you now present? Hello. Gurunda Rao. Gurunda Rao, you are not audible. You are not audible. You have to unmute. Unmute yourself.
Please unmute.
Your voice is not audible to us.
No, actually, he is muted only. Please unmute. Yes. Now you are unmute.
Yes. Yes, Rao Sahab.
Rao sir, we are not able to hear you actually.
Okay.
Can we ask to someone else?
Yeah. Next one is Dr. Vijay Sharma. Dr. Vijay Sharma. I think Dr. Vijay Sharma is not here. Dr.
Hello.
Vijay, yeah.
Hello. So I'm here.
Okay. Now you present on information communication technology and technology to learn the physics.
Yes, sir. Sure.
Yeah.
Just a minute.
Yes, Mr. Sharma.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Parekh sir.
Yes, sir.
गुरिंदर राव जी से बोल दीजिए कि next again you can try. When your voice will be audible, we will make your presentation.
Oh, okay, sir. Okay, he will present.
So is my screen shared?
Oh, now it is not visible.
Is it not visible? Just a minute. Let me try one time more. I think it is shared now.
Yeah, now it is visible.
Okay, fine, sir. Thank you, sir. Okay, good afternoon, everyone. Myself, Dr. Vijay Sharma. I'm Assistant Professor in Department of Physics in Government Mahila Engineering College. And it's my extreme pleasure to present our paper on ICT technology, which is a technology tool to learn the physics. Before to start, I am thankful to Professor S.V. Sharma ji, Principal, and my faculty colleague, Professor Ved Prakash, Rana Pratap ji, Ram Babu Parik ji. So let us start with me. As I have just seen the schedule, so my PPTs are not exactly in the format, but still I will start. So that particular objectives or the themes of this content start with the advantages of ICT in physics classroom, then the challenges, and there are certain conclusions. So start with this abstract first. So as we all aware of that, this physics is the subject that underpins the science, engineering as well as technology, and behind everything which we have to involve in our life, from morning to evening, at every place, we involve the physics. And nowadays, because in the last 2 years, what we are observing is that teacher is supposed to explain physics principles, not physically present in front of a student. He is somewhere else and the student is somewhere else. And we have to explain the physics principle to our students without physically interacting with them. So at that time, there is a big gap comes out. Okay, and there are so many experiments that cannot be explained without seeing the student or the candidate and the response on their faces. So at that time, a particular technology, which is a very popular technology, not from this year, it is from last 2 or 3 decades. But in India, especially, we have to come across this ICT technology. This ICT stands for this information and communication technology. And this ICT technology involves everything. Even though today we are receiving or we are attending this conference only in this ICT mode, because not easy to attend all are to be in physical mode. So this ICT includes all, that is network, internet, computers, printers, mobile, so many things falls in this ICT technology. And when it comes to explain about the physics, then this ICT becomes more important. Many surveys and the studies says that if we have to compare 2 types of students, one, those students, those are attending the physics classes only in conventional mode, as we generally taken, that is chalk and blackboard. And whenever it compared to the students, those are taking the same class with the ICT, including the chalkboard system also, that is conventional plus ICT technology. So there is a big improvement in the physics learning of student, as well as the physics teacher or the physics tutor or the instructor also considered that he is somewhat in the comfortable position to explain that particular phenomena. For example, if I have to take the example of optics, suppose to be I have to speak about the prism. So as we all aware of that, whenever white light strike on the prism, get converted into all 7 colors. There is a spectrum, beautiful spectrum. But the question comes out to be how we have to explain this to a student. So for that particular moment, this ICT technology becomes helpful. Suppose to be I have a digital board in my classroom. So it will be easy to explain draw all 7 colors on the board. So this is just one example. There are so many examples in all branches of physics. By considering them, we can explain physics at a lot. So using this, what are the major factors and what are the challenges as well as resolution for all these? There are so many challenges as well as resolution for this particular teaching of physics using this ICT. And the first point comes out to be the lack of ICT skills. The ICT skill means, as supposed to be a teacher is very handy with the physics. He is the master of the physics. But once he or she is supposed to be explain the physics by using this ICT technology, sometimes he feels uncomfortable due to many reasons. There are a lot of number of reasons because we are not so much handy with the technology. So this is the first and the major challenge. And this is just the attitude of the teacher or the instructor. If we start to use this ICT technology, there is no doubt that we will be able to explain physics in a more easier manner to our students. So the resolution is we have to take more and more training. And it's my pleasure that I have just in last month, RIE has organized an event on using this ICT technology, and I was one of the part of that particular event. And this ICT is just the training to all the students, all the instructors, that this is not a hard to learn us. Just we have to start with this and we will be able to explain and we will be able to use all this technology. The second one is the depth of teachers' confidence using this ICT technology. As already told that if a teacher is able to explain the physics, once he started in class using this ICT technology, he's supposed to be connected his laptop or the mobile with the internet and some other devices available, supposed to be projector or the digital board. So sometimes there are some issues to be connecting this. In between this time, whenever teacher enters in class and he is supposed to be start with this presentation, and somewhat there is a gap, he is not able to be connect on the digital board, or he is not able to be connect with the particular this projector. So sometimes he loses his confidence. So what is the resolution for this is that we have to take an extra time, and before to start with our class, we have to try to resolve all these particular issues. We can also take the help of a resource person, those have already used this one. So this is also can be resolved. The third one is the deficiency of the training in ICT. In earlier time, when an instructor runs into technical issues, they are unable to handle because they are not aware of how to fix it. So how to correct an issue. Sometimes what we observe that we are taking a class on the projector. So sometimes the screen, our laptop is connected to projector. We have to see our performed experiment on the our laptop, but we are not able to observe it on the projector. So there is a technical issue. So who will resolve it? So either we have to make a practice of resolving this, either there should be some technical person available with the institute who can help the teachers to use this technology. So this is all about this particular sector, even though there are some more challenges of funding as well as availability of infrastructure and the professional development. So as I am not prepared all the PPTs, so I will just start with this. So how to use this physics, especially how to interact with this physics demos. So here, these are the certain links, and these are the open online links.
Yes, sum up with conclusion.
Okay. So what I'm trying to say is that there are certain online tools. Those are freely available on the internet, and these are easily available for student as well as the faculty. These are the certain links, and we can go through with this, and just by using, we can explain the physics in a more impressive way. Especially the virtual lab can help in this regard. For this, there is a project of the Indian government, virtual lab. So you can use this to explain our experiment to students. So in last line, I will try to be conclude in such a manner that even though this technology is very helpful, but what I feel personally is that this technology cannot be alone able to explain the physics in a more easier manner to students, or even nor our physical that the conventional way. So what we have to do, we have to use a blended manner in which we have to use our classical physics teaching method, including this ICT technology. So this is all from my side. I am highly thankful to all for giving me this opportunity. Thank you.
Thank you, Vijayji. Is there
Thank you,
any
sir.
question? Is there any question? Okay, thank you.
Thank you, sir. Thank you.
Next one is from Dr. Rijwal Kareem from NCERT. Rijwal ji.
Namaskar, sir. I'm Ritika Anand, sir. I'm going to present the paper on the behalf.
Okay.
I'm just sharing my screen. Please give me a second.
Yes.
Can you see my screen, sir?
Yes, yes.
So once again, namaskar and a very good afternoon to all the dignitaries who are present over here. Sir, this paper has been compiled by Dr. Rajol, Dr. Ashish Srivastav, myself, Ritika Anand, and Mr. Naveen Gupta. So basically the topic is need of ICT in physics, possibilities and limitations. Now, as a lot has been talked about it in this entire session, so I'm not going to talk a lot about why we require, what is the need of integration of ICT in physics. Definitely, we say that physics is an abstract, supposedly it has many abstract concepts, which generally leads to low interest in learning physics, and which we believe it is a global crisis. And something which the pandemic has gifted us is that it has accelerated the process of integration of ICT in physics. So we have tried to say that physics has actually contributed to the development and advancement of this world. So if there was no physics, there would be no ICT. The first computers and programs were actually an outcome of the systematic study of physics. And today we are at a junction where teaching of physics will remain incomplete if ICT is not integrated into it wisely. And we believe that this word wisely is imperative, because there has to be a balance. Now, when it comes to use of ICT in teaching physics, definitely we all know that there is a lot of multimedia content which is available, computer simulation, online labs. All when we talk about futuristic developments, we would want to highlight the use of augmented reality and virtual reality in the classrooms. And when it comes to simulations used in physics learning, I think that has been one of the key aspects of how even during the pandemic, online labs, which uses simulations as one of the techniques to make the children understand even practical work, has been a very important point. And we have also focused on the fact that ICT promotes inclusion. Students which have behavioral intellectual disabilities like dyslexia, dyscalculia, ODD, ADHD, mild autism, and other disorders which fall under this umbrella, which they are going to really benefit from the ICT tools, as individualized educational plans can be designed by using ICT. Having said that, children who are visually impaired, since ICT uses a lot of visual inputs, ICT can be paired with a lot of tactile diagrams, where this can again amalgamate and will definitely promote inclusion in the classrooms. When it comes to limitations, which is one of again a very important part of our paper, definitely we have to look, we can go gaga over the use of ICT and the need and the possibilities of ICT in integrating in physics teaching, but actually the inadequacy of infrastructure, जैसे internet access है या bandwidth, software, hardware, computers, and specifically our focus is lack of teachers training. poor teachers' welfare and morale, which can pose a threat to the process of making ICT an effective tool for teaching of physics. Second very important point is that the simulation techniques used to understand the practical work can never experience the real experience in the laboratory. Simulation is great, ICT tools are great, but when it comes to working with your hands in the laboratory, nothing can replace it. And we really vouch for the fact that ICT can be integrated as one of the parts. How it has to be amalgamated, the new pedagogical processes which have to be designed by the teacher, but it can never replace the real lab work, where when you talk about simulation, children who are doing online practical work using simulation as one of the techniques, they are doing it all alone. But when you do it in the laboratory, 4 children come together, they learn many work ethics like teamwork, like honesty. One child says that, no, I want to manipulate the readings, and the other one says, no, don't manipulate the readings, I'm going to tell the teacher. So these little things, but they work in character building and so many other things which are required for learning of physics. And the third limitation which we have really which we feel is can pose a threat is the open sources which are available on the net. They are multiple. Now when you have so much of data, so much of resources, so much of ICT tools available, it can create a lot of anxiety amongst the teachers, amongst the students, of what to use and how to use. Now for this, bodies like NCERT, SCERT will have to pull in, a lot of brains have to come together and kind of focus and streamline the availability of ICT tools. It is very important, because if there is no guideline, if there is no streamlining, people will be lost. The students and the teachers will be lost in this wide ocean of the tools which are available. So yes, I think in conclusion, I would like to just sum it up and say that it is extremely essential for educators to design an amalgamated pedagogical approach, as the nature of subject is practical based, and performing experiments in the laboratory, doing hands-on project work and research work finds no substitute. So I am an educator in a school, I am a student of physics, and I am a facilitator for physics. So definitely the schools, the government needs to focus on the infrastructural issues. As I said, teachers training is one of the most important our focus points, because teachers all across the country, they might have an access, but how, in what quantity to use it for the maximum benefit of the students is still a question mark. ICT, as we say, it's like, the tools are like fire. You can use it for cooking, or you can use it to burn the whole house. So that is the power of ICT. Using it by training the teachers properly is a huge responsibility of the lawmakers of the country, of all of us together. So yes, we would like to focus on teachers training, and as I said, streamlining of the content is important. And then of course there is no looking back, because ICT definitely can make abstract concepts like quantum physics or nuclear reactors or whatever is happening at the subatomic level so simple and so handy for the children to understand, that it can actually challenge the notion of the students who feel that physics is always an abstract and a difficult subject because they are not able to.
Thank you, Dr. Ritika Anandji, for your nice presentation. Is there any question? Is there any question?
Just an observation for Ritika ji's presentation. It was an excellent presentation, and she opened up all the avenues. And I particularly compliment her for talking about the value of scientific integrity, which is very much essential, particularly for experiential learning. But what I was expecting, and I do not know whether I should say like this, but from the different presenters, I would like to know some experience. We all know these things, what miracle can be done by ICT, how it can take us to the subatomic world, how it can take us to a nuclear reactor. We all know this, but some direct experience about what they have done if these are presented. This is a humble suggestion of mine, because I think all the entire gamut which was opened up by Ritika ji is known to us, with due respect to her presentation, is known to us by and large. But what really can be done under the circumstances and under the compelling situation which exists in our schools, particularly in the rural area and several such other places, that would come very handy. That was my observation.
Thank you
so much, sir. We'll keep that in mind.
So next one is Madam Shivalika Sarkar.
Yes, I'm here.
Topic of presentation is on the use of video-based analysis and coding for solving problems in mechanics. Yes, madam.
Yes, I'm sharing my screen.
Yes.
Okay, my screen is visible?
Yes, it is visible to all.
Okay, 1 minute. Okay, respected principal, Professor Sharma sir, respected chairperson of this session, Rambabu Parekh sir, respected conveners and Ghosh sir. A very good afternoon to you all. Myself, Dr. Shivalika Sarkar, and I'm working as assistant professor in physics at Regional Institute of Education, Bhopal. And the title of the paper is on the use of video-based analysis and coding for solving problems in mechanics. And the co-author of my paper is Mr. Amritanshu Vajpayee. He is the coordinator of Ignited Minds Fitnet Club, Farrukhabad, Uttar Pradesh. The paper actually deals with, we want to have some active learning strategies, and we want to create some constructive inquiry-based active learning methods. So we propose the use of a software which is Tracker, and this Tracker software is very easily downloadable. You can download it from Google, and with the help of this Tracker, you can create your own projects in mechanics, and it is very useful one. And we have also used coding for the same problems that we had done with Tracker software. Coding is a necessary skill nowadays. There is a lot of hype about coding, and it helps to visualize the problems and understand many problems much in deeper cases. And it also reiterates the idea of citizen science concept, and also a no-cost virtual lab, because we can have a no-cost virtual lab with the help of coding. So the main objectives of the paper were to use a video-based analysis software Tracker to perform various experiments in mechanics. And the second one was to use coding to simulate these different mechanics experiments. So we had downloaded the Tracker software with a free video analysis software modeling tool, and you can easily download it. There is manual and automated object tracking available. You can track the position, velocity, and acceleration of the data, and center of mass tracks are also available. And the coding has been done using Python language. And in this paper, we have only given an elementary implementation of the basic nuances of the Python language. And later on, which we can easily expand it to any animations and simulations. And the best part is that the user can input certain data, and desired output can be taken. So it actually encourages self-experimentation and self-exploration of the concept that are involved. So this is a flow chart showing how the Tracker software works. Actually, you have to take a video of the experiment that you're performing, then you have to upload it in the Tracker environment. You have to calibrate and set your axis. You will get a graph of the observations, and then some curve fitting has to be done. And with the help of that curve fitting, you can very easily verify the laws of mechanics. This is the first result. I'm coming to the results. Here I will show you. This is the determination of the value of acceleration due to gravity of a free falling body, and that was performed in a laboratory. You can see this. The video was taken of a ball that was dropped from a height of 1.5 meters, and was captured. The video was captured in high-speed mode. And then this was opened in a Tracker environment. You can see the observations are shown by dots, and then a curve fitting was done. You can very well see that the first equation of motion was used in this, and when the curve fitting was done, you get the value of acceleration of the free falling body of the ball that actually in fact we had used. And these are the coding results of the same experiment that we have shown. This is the velocity versus time graph, the acceleration versus time graph, and with the Tracker we had obtained acceleration due to gravity as 9.94 meter per second. So you can see that with precision we had got this value. The another experiment.
Madam, just conclude your
Okay,
presentation.
okay. So there is a restriction of time. So I have just shown one experiment. So there were in this way we had performed several experiments with tracker as well as coding, and you can see the graphs are shown. Atwood machine, which is very famous, that is shown. Then coefficient of restitution of a tennis ball using tracker, as well as we had done with coding also. This is shown. And then the determination of period of a simple pendulum swimming through small angles was done, and due to constraint of time I cannot discuss on this. The conclusion is mainly that this is a very useful software. Tracker is a very useful software which can help to solve the daily life problems in physics, and it can be easily downloaded, and we can extend these studies to many more experiments like projectile motion, Stokes law, rotational motion, coupled oscillation. And coding, as you know, has helps to visualize many situations. We can in fact interpret many situations. So thank you all for patience hearing, and for giving me a chance to present. Thank you very much.
Thank you very much, sir. Therewith, madam, is there any question? Okay. One presentation was left in this session. ICT in support of physics education. Dr. V. Gundurao sir. Gundurao ji, are you hear me? Gundurao ji, your voice is not coming to us. Please unmute yourself. No, your voice is not coming.
राव साहब, आपकी आवाज नहीं आ रही है।
Rav Sahab, your voice is not audible to us. Please stop your screen sharing. Rav Sahab, please stop your screen sharing. Stop. Okay. So next is I think time is for lunch hour, but we have to just take 2 presentation more. Then we will go for lunch. The first one is on experiential learning as teacher strategy in physics education and its implementation in school curriculum. Dr. R.R. Koirang is here from NCERT. R.R. Koirang ji? Koirang sir? Koirang ji?
Yes, sir. Can you hear me?
Yeah. Just present. Okay.
Good afternoon, sir, for giving me this opportunity. I'll be very brief because you have given a very short time. But this has motivated me, in fact, the experiential learning things. I just want to share and regarding this experiential learning in the light of this NEP 2020, and also in the light of the curriculum, which we are in the process of preparing this, and also through interaction with teachers during these experiential learning workshops and other things. So my topic today will be experiential learning as a teaching strategy in physics education and its implication in school science, in school curriculum. Actually, this topic will be very relevant for science. Basically, I would have loved to, put this title as for science education, but nevertheless, this is applicable for physics also and in general science also. So coming to what is experiential learning? This experiential learning is not a new thing, but it has been very much emphasized by NEP 2020. Now we are going to move towards this experiential learning. But to recap this definition, just to recall, the experiential learning is nothing but it focuses on learning through experience of the learners. And this experience can be the experiences gained in the life of the learner in the earlier event, might not be necessarily today, but earlier time also, and the current or present events in his or her lifetime. And those experiences arising from the learner participation in activities conducted in the classroom by students and teachers. This is what precisely we are doing activity in the classroom. I mean, that is what the third one is that. Now, the key element of this experiential learning is that learner analyze their experience by reflecting, evaluating, and reconstruction in order to draw meaning from prior experience. Now, when we conduct activity or experiment, because in physics or in science, we usually do activity or experiment, but are we really giving them the learners to reflect, to evaluate, and also to reconstruct? Are they really given the opportunity to make meaning from their experience? That is the question. If not, then we need to reorient our way of textbook writing, our way of teaching. Now, going to why experiential learning? Why do we have to do experiential learning? Let us recall some of the the philosophers that Confucius in 1450 BC, in fact, had already coined this term that I hear and I forget, I see and I remember, I do and I understand. So it's basically experiential learning is that I do, then I will understand. That is one. And many of the notable educational psychologists like John Dewey, Carl Rogers, David Kolb, all have emphasized on experiential learning. Why do we have to adopt experiential learning? We call it learning by doing also. So then to recall the national education policy, it has recommended adoption of this experiential learning at all stages of school education, including hands-on learning, art integrated, sports integrated. I'm happy that some paper will be presented, I think tomorrow, on regarding sports integrated physics and other things. In fact, this comes as a part of the experiential learning. So then experiences has an important role in the process of construction of knowledge. This comes from learning theory, basically. The activity we are doing, the experiment we are conducting is supported by the learning theory. So that's why I'm emphasizing on that. Why experiential learning? That's why learning theory support that students learn better. Students can learn meaningfully if we adopt this experimental learning. I will want to skip this one because there is shortage of time. Yeah. Yeah, please. Now why experiential learning again? Now, to adopt this experiential learning, the NEP also recommends redesigning of curriculum and pedagogy rooted in our context. So precisely, we have to draw a lot of experiences from our context to fit in there. So later on, I will come to that. With the system and the need for infusing this context, it is very important to contextualize this curriculum. Whatever physics curriculum, we need to contextualize. Okay, then contextualize is nothing but this is an integral part of the teaching learning process, which involve engaging learners to look deep into their own experiences and connect those knowledge with the content given to the children. Now we need to critically look in what type of content we are giving. That I will come in later on. Now, while doing so, what will be the implication? Suppose we are adopting experiential learning. What will be the implication on teaching learning of science and physics? Now, before we moved, I would just like to remind or recall for all of us that what is science basically, which include our physical science and physics. You know, humans have been very curious about and inquisitive about nature. We all know that. And this curiosity and inquisitiveness have driven them to explore nature in different ways. Now, one kind of response that has been, followed since time immemorial is to observe physical and biological environment carefully, look for meaningful patterns and relationships, and make conceptual model to understand the world. Now, from this meaningful pattern and relationship, which we are establishing, we are arriving at theories, we come at laws and principles of science.
Sir, just conclude it. Koring sir, just conclude it.
Okay, sir. Now, anyway, just give me, sir, two more minutes, sir. Now, if we look at these definitions of science, then we will have to, necessarily provide the learners to observe these patterns, to build relationship between these patterns, and how they can come out with these laws. Then the whole idea of conducting experiment activities, lot has to change actually, not basically, because children have lots of idea about physics concepts or science concepts already there. So how do we arrive those concepts? Through their experiences. Now, what we used to usually tell students is that apply your knowledge to daily life. Rather, we will be talking now more about what is your experience already, how we can arrive the laws of physics, the laws of science theories from their experiences. So that is going to be very key. Oh, I want to skip this. So this will be implication on the curriculum, which I want to share. Now, the NEP recommends that reducing the curriculum to each core essential. Now, we will have to really reduce our curriculum. Now, what do we mean by this core essential has not been defined in the policy document, but what we can understand is that the core essential can be understood in terms of the fundamental concepts or elements which are required for further learning. Now, this is a big research area where each one of us can take up. This is a challenge. What are the core areas in physics which children needs to learn? Now, this would involve selecting themes, ideas, and skills in science and physics. Now, preparing of learning materials, weaving in the experience of the learner to arrive at concepts. Now, you select some themes, concepts of physics or science. You try to identify certain experience of the learner, children, whatever. Then you will be able to somehow be able to integrate many of these concepts in the existing experience of the children.
Koring-ji, just sum up.
Yeah, yes, sir. Now, the way forward is that you have to necessarily contextualize. From experiential learning requires that you should necessarily contextualize your materials. Now, what do we mean by contextualization? Contextualized approach demands that students to look at their world and identify the science within it to develop a deep and understanding of the key concepts and ideas. In this approach, context is central to student learning. That is what it means. And a large number of researchers have summarized the benefit of contextual approach by stating that students respond positive to the task that they perceive to be purposeful and interesting to them. It's related. Therefore, they argue that activities and investigation experiment should be conducted and centered around the context that is relevant to students.
Thank you.
Sir, just this is the last one, the last slide. Sorry, sir, but this is very important. I want to say And for us, the point to ponder right now is that we can take up our own researches in this area. I encourage to you, all of you, if you can think over these researches, which we can do. Contextualization requires that we have deep understanding of the context as well as the concepts and their interrelationships. Many times we cannot connect the context and the concepts. Only we are satisfied with giving only the examples which are given in the text or textbooks. Second is the case for adopting this contextualization is strong, but doing is much more complex and demanding on teachers' knowledge and expertise than it may seem. So this we call it contextualization cage. We are unable to come out. So we need to do a lot more researches in this area. Then given the background of students and teachers as well as local factors and the context which involved, that makes the need of each school quite different. So, and a single roadmap for implementing this is unlikely to exist because we have to work on a lot of individual differences will be there, local, regional, all will be there. So we need to work on it.
Thank you
So much, sir. Thank you so much.
Thank you, Dr. Koirang ji.
Yes, this is Gurnath Rao.
Is there any question?
This is Gurnath Rao, sir.
Yes. So next.
जैन सर कुछ बोलना चाह रहे हैं, अनम्यूट कर लीजिए सर.
I will just try to add a few words.
हाँ राव साहब बोलिए.
Can I speak? Hello.
Sorry for the interruption, sir. Sir.
Please go ahead. Please go ahead.
I will just try to add a few words.
Sir.
No experience, no change in behavior.
Sir, I am sharing my. Sir. Sir.
Sir, Jain sir, yes sir.
Hello sir.
Jain sir, बोलिए. Hello.
This is sir. Sir.
Words, no experience, no change in behavior, no learning. That is the crux of what he has spoken. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you. Yes, Dr. Gundurao.
Good morning, sir. I am sir. Sorry for the interruption, sir. Due to because I am residing at rural.
You start, no problem.
Okay,
start.
sir. Okay, sir. Okay.
Thank you. Thank you. Yes, Dr. Gundurao.
Good night, sir. The main, sir. The main objective of using ICT, as we know, the objectives using ICT to make subject to easy understand the subject and do consideration, bring curriculum, which is the need of the day, as we know. Actually, my intention is to develop a concept to understand how ICT can be used for the students, particularly grassroots level, particularly rural area. So for this purpose, I have chosen some examples with the help of journals and other things. The main objective of this paper to discuss role of computers to understand physics and strengthen science and technology. We point out the role of computer technology, namely simulations, multimedia, telematics, virtual reality, and etc. The method we are adapted, this research is totally meta-analysis method, sir. Actually, the population in the study, books and articles, theses, dissertations, and etc. I have chosen. We know we are having different types of what we can say ICT tools for school level also, and we at up to graduation level, we thesis also. For school level, we are using simulations in our classrooms, in labs, and also telematics also we are using. Virtual reality is to make it. Computer-based laboratories we are developing now, sir. As we know, the telematics generally we are using with various type of internet things and others, sir. Actually, virtual reality we know already we discussed a lot about this thing.
good examples we are using science space and network, Newton's world and Maxwell world and Owen world we are using for students. And also we are planning to develop computer-based laboratories which can be used physical things, sir. And also we are using sometimes we can use using the electric field hockey and group.
Gundarao ji, you just tell what you have done and what is the conclusion. Just you share that only.
Okay, sir. Okay, sir. Actually, we done with the use of ICT and we are making the students towards the physics interest. And also we are using simulation in our schools, particularly class 9th and 10th high school level. We are using. From this, student attitudes are very much changed. And also we are using the different types of kinematics and other things in our laboratory. And we are using to develop the ICT skills in physics we are developing, sir. And it is very, we can say, the use of Clicks learning labs we are using. Clicks learning labs, according to we are maintaining these things, sir. Thank you, sir.
Okay, thank you. So we will closing this session here, and we will meet again at 2:30. We are breaking this session for lunch. We will again meet at 2:30 on the same platform. Thank you.
And who will be the presenter? Please announce the name so that he can be there.
That is Exploring Children Ideas About Solar System, Felicita Gali.
Okay. So 2:30, she will be there to present it, na?
Yes.
Manishu.